Alright, enough slacking, let's get to it. My goal today, one goal. And it's not what's actually up here. Well, it is, but it isn't. The one goal today is to avoid certain words. And not swear words. We can swear as much as we want. Yes. You're what? The cleaning lady is leaving? Okay, what do you need from me? Okay. Alright, so. So is probably another word that I should be avoiding. So, any type of filler word, we're going to try to avoid those words today. Because I listened to one of my previous streams, and it annoyed the hell out of me how much I was using filler words. I would rather have spaces in my speech than fill it with a whole bunch of noise that just annoys the hell out of me, right? Right is also one of my filler words, so I should avoid that as well. And use that sparingly. We'll see how this goes. Can't make any guarantees. The agenda today. We've renamed our sprints. We're still doing the TAUDEPO work. However, I realize it would be best to have 3 other sub-libraries to go along with TAUDEPO. TAUDIRT before TAUDEPO, TAUTYPE and TAUSYNC after TAUDEPO. I explicitly want TAUSYNC to be after TAUTYPE so that syncing with the GPU cannot be done through the TAUTYPE. That is to avoid granular resyncing with the GPU. We want to resync with the GPU once per frame. It doesn't make any sense to have a dirty flag management for item number 11 and then to abuse that by having TAUTYPE automatically call TAUSYNC. So we want this order. This is the order I thought about. This is the order we're going to stick with. Filler word. I see I don't have the right names here. Because I have reordered my sprints, my future sprints, we need to rename the bottom 4 to 5 and the bottom 5 to 6. And we are on sprint number 4. This is integer ID number 42. In other words, the 42nd video since I began serializing all of my videos. And this is the recording for December 14th, year 2020. Okay. And that's also a filler word. It'll take me a while. Let's start stubbing in the needed sub-libraries. Even though TAUDIRT will be a data-only sublibrary, I want to keep to the convention of always having a D file and a F file for data and functions respectively. Lastly, TAUSYNC. I want to keep to exactly 7 letters for every library name, so we're going to put a little checksum above that since I am kind of screwing up, I've seen. TAUDIRT, TAUTYPE, TAUSYNC. TAUDIRT, TAUTYPE, and then lastly TAUSYNC. And we can take this here. Paste that there. Let's check the file names, make sure they match. TAUDIRT, TAUTYPE, TAUSYNC, SYNC, SYNC, SYNC. I am a fan of spelling sync with an H, however, I'm going to keep all the library names to exactly 7 letters, so any weirdness with spelling will be put in there, if that's what it takes to get to exactly 7 letters. Let's make sure the project runs before we go any further. These files are not yet in the project, but before I try to stub them in, I need to make sure the project is in a stable state. I'm fairly certain it's already in a stable state, but it was yesterday when I touched this, so there is the possibility that something went wrong, you know? Maybe I forgot something, you never know. We're good. Let's start stubbing this in now. On one of my monitors, I'm going to make a note of the exact order. TAUDIRT, TAUDEPO, TAUTYPE, and TAUSYNC. Because I know that is the order I want, I'm going to think about enforcing that order with some preprocessor directives to double-check my work. In my library chain, we have these things called include fileboy, include nadykey, right? Includes for every single subsystem. Going with this pattern, if we can only do these checks in the data file because all data is included before any of the function files. And these includes don't specify if it's the data file or the function file. Therefore, these checks are only going to work in the function files, because by the time we get to processing all the function files, all of the include flags have already been used. So, if AAC 2020 include looking at where we set our defines, we notice that we include the file before we mark it as included. So we're going to take advantage of that. And we can reference ourself right here. And this is going to serve as an include guard in a way. That's not the intention, but that is one of the effects. Let's make sure it's actually an end if and not an end. Yeah, it is a end if. And we need 4 of them. It's a little bit bulky. And I could possibly change my mind on this because it is so bulky. However, I like the rigidity that it offers. For error messages, it doesn't actually have to be a string, I believe. It can be anything. I'm just going to write it this way because it makes me more comfortable knowing that this is an actual hard-coded string that I can search for in the codebase. We need 3 more messages like this to distinguish between the messages. We should have some type of way to highlight this. So I'm thinking highlight the one we're currently in. This is really bulky. I'm not a fan of how bulky this is. I have an idea. I'm not sure if I'm a fan of it, but what we could do is create a guard file for this. I usually don't want to fractionate things, so let's assume this is a non-standard type of file, right? We'll put the guard file in here, and we'll call it TAUDIRT.g for guard file. With this guard file, note that we're already inside of the lib folder in libchan, and we need to account for the relative paths when we're gluing things together with includes. Because we're already inside the lib folder in our libchan file, all we have to do is include the guard file like this in TAUDIRT. This adds a little bit of extra indirection, which I'm not a fan of, but it should be something that we don't often have to look at. It should be something that we only have to look at when things go wrong. Therefore, I'm okay with tucking it away like that. Let's do something similar for all of the other systems. We can take TAUDIRT, we can paste it, and for tau type, we can just switch these flags. If we do it this way, it's a little bit easier to always be reminded of the ordering. In tau type, TAUDIRT should have already been... This is actually wrong. TAUDIRT, TAUDEPO, tau type, yeah. Tau type should actually... Tau type will be making calls to TAUDEPO. Already screwed things up. TAUDIRT, TAUDEPO, tau type, TAUSYNC. Looking at TAUDIRT again, TAUDIRT, TAUDEPO, tau type, and TAUSYNC. That is the order. These need to be flipped here. Let's ensure that everything is, in fact, in the correct order, using some token highlighting. That's kind of annoying. The casing has changed the syntax highlighting, the token highlighting, and it's not recognizing the case here. Because of that, we're going to this second error will never be caught, but the idea is to keep identical words like this so that when we are doing token highlighting, we can get... That's interesting. If we use... Let me try a different separator character here. This is a editor-specific thing, so I really shouldn't be too concerned about it, but I am. That's kind of annoying. We're not going to worry about it. But we know that when we highlight these, we can see the correct ordering. The correct ordering is highlighted here. That's kind of nice, because now it shows us which file we're currently in. Dirt, depot, type, and sync. Dirt, depot, type, and sync. Duplicate this. Put everything to uppercase. And check the correct ordering. Looks good. This is getting kind of cluttered. What I'm going to do is I'm going to take all of my guard files and I'm going to put them on the right side. That way, as I am adding the guards to the different data files, I can keep track of them all, right? Because there are 4 of them. Let's order them in the correct order. So, TAUDIRT. We need to open up TAUDEPO, which already exists. TAUDEPO.data. And TAUDEPO is right here. TAUDIRT, TAUDEPO, TAUTYPE, and TAUSYNC. Let's add the includes for each one of these. We have this nice comment here at the top of the file. TAUDEPO.g. The guard files are included. Dirt, depot, type, sync. We need a depot guard file. The depot file has the correct guards. I may have gotten TAUDIRT incorrect or TAUTYPE. Let's look at those. All zeros. This one's flipped. Now we expect 2 to be flipped. We're inside of TAUTYPE now. make some notes. It's not necessary to get this decorative, but I like to take my time and make sure everything looks nice. We have these orderings here. TAUDIRT, TAUDIRT, TAUDEPO. This is TAUDEPO. Therefore, this should be capital. TAUDIRT, TAUDEPO, TAUTYPE. We're missing one. We need TAUSYNC. Flip this flag. We're on the last library for the Tau collection. All of our guards have been added. We should scroll through these. This is concerning. My syntax highlighting has not been applied to this file for some reason. Let's rename it, make sure there's not any spaces in the file. That's the correct extension, ._. I'm not sure what's up with that. Looking at these, let's analyze these flags here and see that they animate correctly when I click through all the tabs. Flip, flip, flip. The last one isn't flipped because this is the one we're currently including. Let's look at our main C file and see where everything is. We have this 2D for tile cam. That's actually going to be inside of TAUTYPE. TAUDEPO is right here. Ooh, mistake there. We need TAUDIRT here. And two insertions after the depot. TAUTYPE and TAUSYNC. We'll need to renumber. For consistency with everything else I've written, I think underscores for the summary makes sense. And 24. This was the current max. We've added 3 libraries, therefore the max should now be 24. And we see a 24 there. 24. It's going to be more effort than that, though. We need to edit the library chain to accommodate these new libraries we're stubbing in. It's going to be a little bit weird because we have an insertion here and then an insertion here. I think the best way to approach this will be to copy-paste where we knew the new libraries, and then rename the numbers once everything is in place. I'm going to copy this for reference here and put it on one of my monitors you can't see, so that when I am refactoring, I'll have it for reference. Let's look at the library chains. The library chains are basically my build system. I have a very strict ordering where I keep a iron fist on my dependencies and the compilation order. I don't use dependency injection. I don't use lazy initialization. I make sure I have a clear understanding of my project and how every single piece goes together. If I'm using dependency injection or lazy initialization, it's a sign that I don't understand my code base. It also makes things a lot more complicated. I want the project to always compile in the exact same order every single time without fail. When you dependency inject or lazy initialize, adding a new system into your project can drastically alter the initialization order because of the way the dependency graph needs to be resolved. We're going to need to go up to 24 now because we added 3 extra libraries. So we'll go 1, 2, 3 with Control D and Notepad++ to duplicate the lines. Fill in the numbers 21 to 24. And set that to 24. Make sure that the ones place is directly in the center and that the tens place is over to the left. We need to be precise because we are going to sometimes put our macros in multiple places and we don't want redefinition errors that are from the formatting. For example, this defined as this and defined as this may count as 2 different defines. I'm not sure. But to avoid that problem altogether, let's just be highly consistent about how we do this. Let's find pixname in our list of data files to include. Pixname is where we decide to put all of the data chunks for all of the editors. The pixname data pieces that are in the file scope memory are actually GPU data types, except we've decided that GPU data is a temporary container that we populate on the fly when we need to pass around pixname variables. The reasoning for that was I wanted a centralized location for all the different variables for the memory that's managed in the program, and I wanted it to be a nice flat list as simple as possible where I could just have a nice overview of everything that's there. And if I were to try to do such a thing with instances of GPU data that live in file scope memory, it would be much more difficult, as I would have to use static initializers in the class, or in the file. Sorry, it's not a class, it's a struct. So that's why, and maybe it's kind of an awkward design choice, but that's what I've decided to go with. While we're here, let's clean this up. Pix name is no longer a pattern breaker. GPU data is not limited to graphics is a correct comment, so we can keep that. We really only need to know what comes after pix load, because that's when we have TAUDIRT, TAUDEPO, TAUTYPE, TAUSYNC, and then paint 5D. Pix load, and we need TAUDIRT before TAUDEPO. We know that TAUDIRT is 20. TAUDEPO is 21. Paint 5D is after all of the Tau files. We'll take TAUDEPO and paste it 2 times. And then rename the numbers and files accordingly. TAUTYPE, TAUSYNC. We have to shuffle all of the numbers downward. Oh, we've already made a mistake. This says TAUDEPO. This, TAUDIRT. Well, that was some luck. TAUDIRT, TAUDEPO, TAUTYPE, TAUSYNC. There should be 20, 21, 22, and 23. 20, 21, 22, and 23. Dirt, depot, type, and sync. Dirt, depot, type, and sync. It may be kind of tedious, but the code will be much clearer if we take the time to add this rigidity. Lastly, before we continue on to the function section, it's a good idea to make sure that these numbers match. 24, 23, 22, 21, 20, 19, 18. We don't have to go any further up than that. We've only made the changes in this area. That should be fine. We need to do the same exact thing for the functions. All of the functions are included after all of the data. That way we avoid artificial dependency loops. An artificial dependency loop would be where class A depends on class B, and class B depends on class A. Typically, when you have something like that, you actually don't have a dependency loop, because it's very likely that class A uses classes B data, class B uses classes A data. But because you're using classes, you've tightly coupled your functions and your data, and now you're paying for it. We're not going to tightly couple functions and data like that. All data comes before all functions. We're looking for pixload now. Pixload should be 19 according to my notes. This is TAUDEPO. We know we have 4 tau files: dirt, depot, type, and sync. Therefore, we'll take this, we'll put a bookmark here, and we'll paste it 3 times. We'll put bookmarks at the sites that need refactoring. We'll now reorder the numbers 19, 20, 21, 22, 23, and 24. After renaming, we also need to rename the library names. Dirt is first, so TAUDIRT for dirty flags. Depot is second. TAUTYPE is third. And TAUSYNC is fourth and final. Let's double check the numbers. Make sure we didn't forget anything. That looks good to me. Lastly, let's double check all of the names for the libraries we've just included. We did a lot of cutting and pasting. Let's make sure that all of these highlight to unique colors. Cyan, orange, yellow, and purple. And if we scroll up, we should see the same thing in the same order. Cyan, orange, yellow, and purple. I'm confident that we've stubbed this incorrectly. We'll now go over to libchan bot, which has another redundancy to make sure that everything has been included in the correct order. We want to take a look for pixload in this list. We see pixload here, and we see TAUDEPO here. We're going to take this block and we're going to duplicate it 3 times because we have 4 tau systems. We'll highlight TAUDEPO so we can see where those changes need to take place. TAUDIRT is first. Depot second. Type third. And sync is last. A lot of these redundancies are not necessary. However, it gives me sanity of mind that all of the libraries have been included in the correct order. We'll take TAUDEPO, paste it 3 times once again. We will highlight TAUDEPO. We'll renumber. We know the first is TAUDIRT, and that should be 20, 21, 22, 23, and finally 24 for Paint 5D. We'll then rename. TAUDIRT for the dirty flags comes first. TAUDEPO. TAUDYTE, and TAUSYNC. I'm confident that those are now in the correct order. But if we want to be extra careful, we can once again use our token highlighting, get 4 unique colors, scroll up to the top, also see the 4 unique colors in the correct positions. Scrolling down, we want to clean up some of our macros for other people who might want to use this library. Duplicating 3 times and renumbering. We know this is TAUDIRT, TAUDEPO, TAUDYTE, and TAUSYNC. If I didn't already go over it, the reason we have TAUSYNC as the last library is so that tau types cannot resync with the GPU. The reason for that is I want to enforce only resyncing with the GPU once per frame at most. If TAUDYTE is allowed access to TAUSYNC, then TAUDYTE could potentially, within its getters and setters, be resyncing every time we set something, which would be a horrible design. By enforcing this strict ordering, we ensure that is not going to happen. TAUDEPO does a lot of math for looking up the different cells for where to put the actual data on the texture allocated on the GPU. Therefore, it probably should take some of the results of those complicated lookups and put them in TAUDIRT. Therefore, TAUDEPO will need to reference TAUDIRT. It is a little bit strange because TAUSYNC is going to use TAUDIRT, and TAUDEPO also uses TAUDIRT, and then you kind of have TAUDYTE kind of like embedded in the middle of this, affair between TAUSYNC, TAUDEPO, and TAUDIRT, and there's just TAUSYNC, and there's just TAUDYTE sitting in the middle of that, and that does seem kind of odd, but we're going to keep that order because this order just makes the most sense to me. If I ever question why I did this order, I can reference this video, and I'll know why. With that, I'm in a pretty good position to say everything is going to work. However, we should also edit the F macros. And for consistency, we should what needs to be initialized and what doesn't need to be initialized. I'm not quite sure. So let's think about it. So out of our systems, TAUDEPO already needs to be initted, and I already have that code in there. TAUDIRT should be a data-only library. Therefore, we're going to have an init none function to explicitly say we don't have any initializers. We have no functions. Here's my function that says we have no functions. TAUDYTE. TAUDYTE should actually be a function-only library. Therefore, there's no data to init. TAUDIRT, though it's data-only, the data doesn't need initialization. It's all statically initialized. Let's not say static. Static tends to mean private in C code. TAUSYNC. I don't know if this needs to be initted. It should be a function-only library. I'm fairly confident that TAUSYNC depends on TAUDEPO being initialized, but TAUSYNC itself does not need to be initialized. So this is what we're going to go with. I'm going to put this on my other screen so I can reference it while I'm working on this. Let's put the fmacros bot on the right and the top on the left. Fmacros is my way of cutting down on the bloat from all of these include guards. We're structuring our project so that we can compile up to any point in our library chain and have a working project. That's so if we ever run into problems with our code, we can binary search by recompiling the project at any point and seeing if the weird, mysterious, bad behavior goes away. For example, if we are doing a memory stomp, or we have some type of memory coherence issue, or any type of weird behavior that's very hard to debug, we can split our project in half, see if there's a problem. If there isn't a problem, we'll split downward and search, recompile here. If there now is no problem, we'll split again between the point at which we had a problem, the point at which we didn't have a problem, and recompile somewhere in the middle. And we keep on doing that until we find the transition point between where a problem happened and a problem didn't happen. Let's say that we compile only up to libchan 8, and we have a problem. And we take a step back and we compile only to libchan 7, and we don't have that weird, strange problem. Then we can be confident that there is some type of bad code in libchan 8. If we're lucky, that library is relatively small, and we won't have too much work trying to dig out where that problem is and where that weird code is. The smaller we keep our libraries, the more benefit we're going to get from this. All of our libraries should be relatively small because we are abiding by the do one thing and do one thing well principle. We know there's already an initializer for TAUDEPO, so let's search for that. We can see that TAUDEPO is in our list of auto-generated init functions. All of our other libraries that are tau-related are going to be no init functions. These are loop tick functions, and somewhere we have a section for init none. Yes, init none. We've already been auto-generating these. We might as well keep up with that pattern. TAUDIRT has an init none. TAUTYPE has an init none, and TAUSYNC has an init none function. Looking at this, pixload, CPU info, both accounted for. Our 3 new ones are here. Let's delete this. We're going to copy all of this information here, and we're going to use our shortcuts to auto-generate some code. Now, it can be a bad idea to auto-generate code like this, because then you get like a whole bunch of bloat like this. And Java is really known for doing stuff like that, for auto-generating getters and setters and all that other kind of bloat. I want to use this kind of sparingly. And here's a good place to use it, because the fmacros file is really used to hide the bloat that is what we're looking at right here. The idea is, depending on what we compile up to, different functions may or may not exist. If we haven't compiled up to pixload, then its init function will not exist. So we'll use the macro down here. If we have compiled up to pixload, then its init function does exist. So we'll take this macro and we'll replace it with the actual function name. Macros are kind of scary things, and whenever we use a macro from another file, we absolutely want to make sure that the word macro is somewhere in the name of that macro. Because the worst thing about macros is dealing with macros and not knowing you're dealing with macros. fmacros is actually a namespace, noted by the fact that we are in a file called fmacros. The purpose of that is to make it so when we find a macro from another file, and we know that it's a macro because it says macro in its name, we can also figure out easily what file that came from, because the name itself is a namespace. All namespaces are exactly 7 letters. To avoid getting function names that are too large, for the actual function, we kept the Atomic Alice C 2020 namespace, and then just swapped it out with the word fmacros. And then this part of the function name is the same for the macro version and the actual function name. I'm confident that that looks good. We can do a double check to just make sure everything was auto-generated correctly. And we see 5 unique colors. Therefore, we're good. Looking at fmacros bot, we undefine some things, but we don't undefine everything. Some of this is kind of hard to keep track of, because some things have an init, some of them have an init none. What we could do is, rather than only do the exact things that actually have functions, we could undef things that don't even exist, and I believe that would be fine. However, then we don't really know what has what. And these undefines can kind of serve as a list of categories, right? With that said, we know that after pixload, we have 1, 2, 3 tau libraries that have init nuns. The first one of them being TAUDIRT, then TAUTYPE, then TAUSYNC. It may be beneficial to isolate them like this. I don't know. We may be missing some macros that we should be undefining here. For now, I'm not going to worry about it. But we'll save that later for maybe a cleanup pass. Let's take a look at how much time we've been doing this for. So 1 hour, right? So a lot of this is very tedious, right? Taking 1 hour just to stub in functions where they belong. Now, while that may be tedious, we have to think about what are our priorities here. One of my higher priorities is to have very rigid and clear code with minimal abstraction. What I'm doing here adds a lot of rigidity to the code. It's not that easy just to like add a new library and just shove something in somewhere. And because it takes a lot of effort to just shove something in there, we have to take more energy and serious consideration before we shove something in there, because it's not an easy task. And that is by design. The last project I worked on, or when I worked on Atomic Alice 1, it was very easy for it to make a new class, and I would like make multiple classes every single day and add all these new features, and then you just get this explosion of just way too many little helper things that do helper function classes that are only used in one place, and little tiny other utilities. You don't want that kind of proliferation. Yes, you do want things to be granular enough where every single sub-library does one thing and does it well. However, you don't want to be so granular that you have all these things and you start to just lose track of what's what. So it's kind of weird, because you want these like broad categories, but then you don't want the library's name that's a broad category. You don't want it to do too much, yet you want it to be a broad category. And that's kind of tricky to find that kind of balance. But like I said, that's why we want to think about it, and I literally thought about it all day yesterday, because I wasn't allowed to do any work yesterday, to think about what new systems I needed and what order they should be in the chain. Now that we have all those things stubbed into place, we should be able to, we can close this. This is just to keep my hard drive running, but since we're streaming, we should be okay. So, actually, let me, there. Let's give it a run. Static assert. So is one of my filler words, so, goddamn. Trying not to use any filler words today. Static assert. In F macros, I'm not certain this was a good idea to add static asserts for all of the loop tick functions, but that's what I decided to do. And for any region of code that is doing the same thing, I want all of the blocks to be identical, like in pattern. Therefore, even though I think this is a bad idea, I'd have to get rid of it with all of these other ones, and I actually like the extra rigidity and extra security it gives me. So therefore, I will keep it. Looks like we don't have any compile errors. And the project's running. Cool. Now that we've stubbed everything in, let's look at our agenda. Stub in TAUDIRT, stub in TAUTYPE, stub in TAUSYNC, enforce order. We have... We're still not on sprint 5, though. We actually have to write the logic for all of these. What I'm going to do is I'm going to take 14 and I'm going to delete it, and then this will be 15, 16, 17. You'll see what I'm going to do. So I'm going to take this list, and we're going to say that 11, 12, and 13, and 14, they're actually done. So now we have items 15, 16, and 17. 15, add code to TAUDIRT. 16, sorry, 15, add code to TAUDIRT. 16, add code to TAUTYPE. And 17, add code to TAUSYNC. Now that we know that, I'm going to put this list on one of my other monitors, so I have this agenda in mind as I'm working. It'll be for my reference. Let's go open up TAUDIRT. First, let's close all of these, get a fresh slate. Data on the left, functions on the right. TAUDIRT is a data-only library. However, we have an init none function for this. An init none is just there to make it easier to account for all of these systems when looking at the main file. We've been adding init nones quite often. Therefore, I think it would be a good idea to create a snippet for this. Because we've just been doing it so many times, I think it's about time to just have a snippet for this code. Hold on, taking off my sweater and stuff. We also want to keep a section divider as well, so that will be part of the snippet. Now that's weird. Oh, it's not include, it's define U32. Now that I know that's define U32 and not include U32, we're going to go over to our snippets right here. And for next time, if I say include U32 or U32 include, I'll make a note that that's what I meant. We could also do it with other types, so we could open up a template, and we can take this U32 as the source, and we can look for U32, and when we find U32, we're going to replace it with itself, and then some other commonly used types. Let's cover them all. We have 32-bit. We don't use 16-bit, but we do use 64-bit, and we use 8-bit. 64, 32, and 08 for 8-bit, unsigned and signed versions. With all of these replacements, let me add a little bit more, since we have room to... Since we're going to leverage the auto creation of these shortcuts, we might as well add some more, you know? That looks good to me. So we're going to take this. And now we have shortcuts that are going to remind us of the correct command next time we say include when we actually mean define. And I know why I used include. It's because in order to get access to these types that we're using, we have to include the stdint header. And you use the include word to include a header. Therefore, it's an honest mistake to make. Well, I mean, what would be an unhonest mistake to make when you're trying to code your own library, right? undefine any local defines after we're done using them. It may look a little bit crazy to do it like this, where we define and then immediately undefine, but the idea is to make sure that our defines never get out of hand. We never have a ridiculous amount of defines at the top and bottom of a file, because we do it on a function by function basis. So even if a function gets out of hand, where we're just throwing a ton of defines all over the place, it's only the function that's out of hand, it's not the entire file. Also, when we're declaring macros that don't have the word macro in them, we want them declared relatively closely to where they're being used. Because the worst thing about macros is them being macros, but not knowing that they are macros. Now that we have this, we should give it a quick run and make sure we haven't made any syntax errors, as we are going to use this whole thing here as a template for a snippet. And it would be nice not to have any syntax errors in our snippet. It's a relatively straightforward, do-nothing kind of function, but I'm known to make really stupid mistakes. Now that we have this as a snippet, or almost a snippet, we're going to look for the TAUDIRT token, and it's only in one place. And we're going to replace it with 1, 2, 3, 4, 5, 6, 7, because all of the sub namespaces are exactly 7 characters. We're going to use stars, so that way, if we put this in a file and we forget to replace this, it's going to give us a compiler error. And also, because of the way our editor highlighting works, we can just double-click this and then, type what we need to type, right? This is a library-specific snippet. I'm not sure exactly where we're going to put it. We could look in AA2, and it does look like we have an AAC 2020 folder, so there's been multiple iterations of this library in different languages, different prototypes. I finally decided on C. Therefore, we have a folder with a whole bunch of diagrams and design notes and whatnot. All of these are not part of the library I'm working on. This is external information. Shouldn't be important to anyone else working on the project. It's more of personalized tools to help me operate in this code base a little bit faster. This is an init none, so let's call it init none. And if you notice I use underscores for file name extensions, that's just because I'm tired of dealing with file name extensions. I'm going to have one file name extension for everything. And the only thing I really care about highlighting are my comments. That's because when I want to focus on something, I'll add highlighting manually to that section. Otherwise, I like to keep everything kind of plain. It just makes it a lot easier for me to focus if everything's not lit up in fancy colors. In my shortcut file, we'll take the path to the shortcut we just made. And when we type a shortcut phrase, it will paste the file contents into the editor we're working in. That should be enough synonyms to where the next time I look for it, I'll be able to find it. Though maybe init none like that might be good. And that should be good. That's probably more than what is needed. Now that we've stubbed that in, we should also stub in the other initializers. Let's look for tau. TAUDEPO is already covered. TAUDIRT is the one that's currently open. We can reopen it. TAUSYNC and TAUTYPE. Let's open up all those function files. We can copy this. We don't need to use the snippet since we already have it right at our fingertips. We're going to paste it here. And then we're just going to rename to the correct namespace. So this is TAUSYNC. This is TAUTYPE. The purpose of these functions is to explicitly show that there is no initialization logic. We want to be explicit with what we do, but we also want to be explicit with what we don't do. This will ensure that people don't think we forgot an initializer. People will see that there's a init none function and realize, oh, this function has no initialization logic. The name init none is actually very intentional. It's so that if we search for, say, this phrase here, right? If we search for an init function in the code base, it's going to find the init none function. Therefore, we don't want to name this no init, because then that would wreck the capabilities of somebody searching for an initializer and then stumbling upon the init none. So there's a lot of considerations to think about with our variable naming. We want a descriptive name, but we also want to think about how is somebody going to navigate around this code base and find things. The most challenging part of stumbling into a new code base is getting your bearings. And we want to think of ourselves as guides or stewards of the code as we are writing this, so that if we get somebody on our team, they'll be able to figure things out and know where everything is in a relatively short amount of time and be able to get up to speed quicker than they would otherwise be able to get if there had not been such considerations in mind for them specifically, right? We have considerations for people who are unfamiliar with the code base. So it's not just about being clear, it's also being friendly and inviting to people who have never seen the code before. You could argue that my code isn't friendly to outsiders because I have these very terse naming conventions. However, I'm not going to break on that. I think the way I'm doing it with the normalization of all my variable names is going to be very helpful for the kind of rigidity I need in my code. Now that we've stubbed those functions in, let's give it another run. This will only give us a compiler error if we make a mistake, and we're good here. The next thing we need to do is we need to go into our main functions file, and we need to add the calls to the new systems. So if we look for, in the root of our project, we have D and F. Kind of ambiguous names, and they are ambiguous for two reasons. One of them is when somebody is new to this project, opens it up, I want the first place they look to be this C11 file. It's the only file with a C11 extension, and we know the project is in C. Therefore, the only file in the entire project that is a C11 file is this. So it's the only thing a C programmer has to grab onto to be like, oh god, where do I start? Well, this is the only C file. Let's open it up. The D and F file are also in the root because it's the main data file and main function file for this C11 file. You could consider this, this is basically our main loop. Our initialization and our main loop, all of our glue code that takes all those sublibraries and puts them together, it's in the D and F files. And because they're these main files and they're used highly frequently because they're top level, I gave them these very shorthand names so they don't take up too much room when I have them open in my editor, because I anticipate having them open quite often. Not as often as I thought, but often enough that it matters. Within our function file, we have a section where we're calling the initializers to different subsystems. Note here we have a do not extract and control F help. This is an intentional comment put here so that when we're trying to see where these initializers are called, we can actually find them. Because we have this indirection with this F macros here, and that's going to make it a little bit hard to find the actual call sites for these functions. Therefore, to ease ourselves into that, we cut and paste the actual function names up here, just to make it easier for anyone trying to search through the code base. We know we need 3 more calls right here. We'll duplicate 1, 2, 3, and then we'll rename we'll rename based on what the systems are called and the order that they're in. I lost my notes that I was looking at, so let me get organized on my other monitor for a second, so I have some reference here. TAUDIRT, TAUDEPO, TAUTYPE, and TAUSYNC. That's the order we're going in. So this will be TAUDIRT, which is a data-only class, so therefore it is an init none. Init none will take a 0. TAUDEPO is second. TAUTYPE, TAUSYNC. Both of these are init nones at the moment. We may change our mind on that, but for now, I think it's a pretty safe bet that there's no initializer code for these. And we'll mark it as a 0. So we have a nice little list right here where we can see where things have initializers and where they don't have initializers. And even if we forgot that something doesn't have an initializer because we put the none at the end, and if we search for an init function, we'll stumble upon the init none with no problem. In our control F help, we want to copy and paste 1, 2, 3 times. And we will take the names here and paste them up there. I'm not certain about the numbering here. And I'm sure this needs a little bit of cleanup to where some things may not be accounted for in here. However, well, why don't we take a look at that, right? Since we're here, let's make sure that all of these systems are accounted for and that they're all accounted for in the same order. Now, this is kind of tedious, and you might think, well, we could just glance at it and we wouldn't miss it. And you would be right. 95% of the time, we don't need to go this slow. However, it's that 5% of the time that you don't go that slow, you screw something up, and you start pulling your hair out later because you can't find a bug in your code. So we're going to go slow, we're going to go steady, and work up to creating something of a very high quality. We're going to, just as it would be ridiculous to eat 1 grain of rice at a time, it's also ridiculous to scurry around like a mouse. What do I mean by that? I mean, think about the food chain, and when you require more energy, you usually have to consume other things that consume other things that consume other things. When we're thinking about I think it's called it's like in biology, I think it's like the energy pyramid or something like that. I don't know what it's exactly called. Let's take a look and see if we can find it. Energy pyramid. I'm going to search for energy pyramid biology. I know I'm on a tangent here, but energy pyramid biology. Are they called trophic levels? Here's a literal energy pyramid, but maybe it's properly called trophic levels. Let's take a look at this, and then we'll explain why I'm looking at this after we have looked at it, right? Takes me forever to code. 3 minutes is not that much to spend on a little tangent here, so let's take a look at this.
Being transferred. Energy from every day in nature, energy is being transferred. Energy from the sun is transferred to these plants. And then insects may receive energy from the plants. And then a snake may receive energy from an insect. An energy pyramid is a display of energy flow in a community. The different levels represent different groups of organisms and where they receive energy. Welcome to Moo Moo Math and Science and Energy Pyramids. Let's take a look at an energy pyramid in a typical ecosystem. You will find producers at the bottom of the energy pyramid. Examples of producers are plants. Plants are autotrophs because they use sunlight and photosynthesis in order to produce glucose, which can be converted to energy. They do not rely on other organisms for energy. Plants take sunlight plus carbon dioxide and water to produce glucose and oxygen. Plants make up the base of an energy pyramid. The next layer includes primary consumers. These organisms are herbivores because they eat producers or plants. Examples are insects, cows, horses, and any other organisms that live exclusively on plants. The next level includes your secondary consumers, which include carnivores or omnivores. Carnivores consume primary consumers, and omnivores eat producers and primary consumers. Examples include frogs, lizards, many snakes, and many birds. Above the secondary consumers are tertiary consumers. Tertiary means third level. They consume secondary consumers. This level includes carnivores. Examples would include wolves, lions, and this hawk. Each layer of the energy pyramid is called a trophic level, and as you move up each trophic level, 90% of the energy is lost, much of this to heat, and only 10% is transferred to each layer above it. If you'd like to know more about energy pyramid,
all right, well, let's since we're watching this,
help. And as always, Moo Moo Math uploads a new math or
okay. Since we looked at that, we should probably be nice and take the URL for this and put it into a tiny URL so that if you're watching this, you can easily get to it. So this is the trophic level pyramid. Don't worry, like, I'll get to the point of this. Like, there is a point for why I'm going over this. There we go. So if you need to watch this, if you want to watch it on your own, go to tinyurl.com/tl-pyramid, and that'll show you the video we're looking at. So how does this relate to our code? Now they're talking about energy loss, but there's something else to think about here. We can get back to the different animals here. With a cow, that cow would be like in primary consumers. For a cow to get energy, how often do they have to eat? They have to eat all the time. For producers, like plants, well, how fast do they grow? How fast do they move? How much energy do they actually have, like on the individual level? And the answer is not much. They can't move around like humans because they don't have that potent of a fuel source. So even though there is energy lost due to thermal dynamics, when you go up these different levels, each level above controls more energy. It's literally a pyramid scheme. Here's your people at the top who basically have control of everyone at the bottom. The tertiary consumers here have maximum leverage of energy. In the same way, we want maximum leverage in our code. Now, think about the difference between a predator here and over here, a prey. A prey animal, like a mouse, is always scurrying around the place, panicking, trying to get food all the time. Whereas your predators here, they're mostly lounging around, and then every once in a while, they need to go on the hunt, they kill something, and they eat it, right? So there's a lot of leverage here, and also, importantly, the way they move is they're not always scurrying around all over the place. When they make a move, it's a very big decision with a lot of energy behind it. So when we're thinking about the way we want to write our code, we want to write nice, solid code, and the number of actions we're going to take are going to be much slower. But they have a lot more leverage in them, a lot more energy leverage, right? If we make this code solid and we make it well, then we can afford to move at a much slower pace because of the amount of payout we're getting from it. So rather than kind of scurry around and panic like a mouse, we want to be like a lion or a wolf. Or, we could be like we could be down here, but instead of being a mouse, maybe you still want to be like an elephant. Where, once again, you don't scurry around, you move a lot slower, but the actions you take have a lot more leverage behind them. I don't know if that analogy makes perfect sense, but when we're talking about the philosophy of how I'm going about that, hopefully that helps for people to understand why I'm coding in the way I code. I could be completely misguided, but the only way to know for sure is to give it a shot and have the natural selection of the world kill me off or let me reproduce. And when I say kill me off or let me reproduce, I mean if the code's good and it leads to something awesome and it leads to a product, then we'll assume that I'm not completely full of shit. If it becomes a failure and we end up with a code base we can't use, then we'll call that a failure. I think I kind of screwed that up. Did I say call it a failure both times? If this code can propagate and reproduce, then it's a success. If it can't reproduce, it's a failure. Now the problem with that is the metric for what determines if code reproduces or not. Well, the only metric that decides if code reproduces or not is if it reproduces. There's no other metric, right? It's the criteria for reproducing is reproducing. And therefore, that doesn't mean the code necessarily needs to be good. We would hope that the code needs to be good for people to copy it and people to use it in other places and for people to use my methodology. However, really the most prolific practices are just the most prolific practices because they reproduce well. And though we would like the reason for the reproduction to be some type of competence, that's not how natural selection works. We would like it to be that way, but that's not. When we say survival of the fittest, that doesn't mean the best. That just means survival of whoever reproduces the best. We can see the same kind of problem in academia with research papers. There is a saying, I think it's called publish or die. And what happens is a lot of academics have to spend a lot of time publishing papers, because if they don't publish papers, well, the only metric that they're being measured on is publishing papers. And if you don't have published papers, you're going to fall behind in the competitive rat race. And if the metric is just publishing papers, then actually doing something and making progress in it takes a back seat. It's similar to getting good grades in college or high school, right? The intention is that you learn something, but you're measuring grades, which is an indirect measure of having learned something. So a lot of times, you may find that though the intention was there, though there's good intentions in place there, you may find that sometimes you'll be playing the wrong game. The game you'll be playing is get good grades, but maybe the game you should be playing is learn, right? For example, at my college, we were taught if you're getting all A's in your classes in college, then you do not belong here, right? Because we went to a technical school, and the thought is if you are able to nail A's in all of your classes, the dean of the school, literally the dean of the school, said, if you're getting all A's in your classes, leave the school, because this is a technical school. If you already are up to a professional level being all A's, then get out of here and go get your job. That was the philosophy, and that is why our department, the art department, had a 80% dropout rate, because everything was literally just ridiculously hard. But I do like that philosophy. I mean, it doesn't look good on transcripts, that's for sure, because, you know, the currency of grades, our currency is very deflationary at DigiPen, right? Where your grades, right, a at DigiPen is, you know, I don't know, like a A+++ in some other school. And when a recruiter's looking at that, they're not going to understand that. Unless you're actually, you know, going to work for a video game studio in, say, California or Washington. They'll understand that, and because DigiPen has that reputation in that area. But, you know, when you try to get a job in a different sector, say like business programming, you can forget about mentioning any of that stuff. They're just not going to understand. But it's good, right? Because the idea is to focus on learning, not to focus on the grade, right? And learning, and when you have a curriculum as hard as DigiPen, you have to decide where you want to focus. Sometimes you have to decide, is this class really what I want to do professionally, or do I want to put more energy into another class? And because you're being so swamped with work, you gotta be like, there's no possible ways to get all A's because we're being swamped with so much work. We're doing work all the time. Therefore, we're gonna decide to get a C in this class because we don't really care about this. This is not what we want to do professionally. And we're gonna move all our energy into this one class that we do care about, and we're going to get good grades in this class because this is what we actually want to learn. And there's a limited amount of time. We got to make a choice on what we actually want to focus on. And in real life, you can't have it all. You gotta focus on what you think is important to you. It would be nice if we had like unlimited time, unlimited energy, but we don't. Therefore, you got to figure out what you're going to focus on. And I'm ranting. Let's keep on going. So since we've kind of lost track of where we were, let's just give this another shot and make sure that everything's actually running, because it might not be. I don't know. Okay. That looks good to me. Also, what I failed to remember, in our library, we've added this thing called Silence, which manages the logging for different systems. We don't want to overly pollute our code with logging messages. Therefore, we want a centralized place where we can turn off logging messages for different systems. See that TAUDEPO has a to-do message. We'll copy this 3 times, and we'll put in stubs for each of the system within the order that they occur in the project. Some of these are data-only libraries, and we'll put stars next to the data-only libraries that should not have any logging messages. TAUDIRT should not have any logging messages. TAUTYPE probably does have logging messages, and TAUSYNC also has logging messages. So we'll keep to-do here's and we'll keep underscores here. And this is, we've stubbed in the data, but we're not actually using it in any logging messages yet. Going down here, we need to take TAUDEPO, duplicate it 1, 2, 3 times, and once again, paste over this. We're going to leave on all of these new systems. The systems that we've already given our attention to are off, which means we're not going to see any logging messages from them. If we end up with a problem in one of these systems, or we want to fix something about one of these systems, we can turn the logging on for that system. But we only want to see logging for the new systems. Let's give that a shot. Let's give that a run. Make sure that everything is still compiling. And if everything is compiling, we're going to push up our project progress to GitHub as a little checkpoint, right? That looks good to me. So we're going to open up git bash and push this up to GitHub. Or actually, git status first. See what we have. Make sure that there's nothing that looks out of place. Nothing looks out of place, so we're going to do git commit-am. And let's look at our agenda so that we can name the commit based on the agenda. Going back to our screen, we're going to call it sprint 004 stubbed in TAUDIRT, TAUTYPE, and TAUSYNC. That's a good commit message. Looks like I forgot to add the untracked files. Let's do a git status again. Or, that's not a git status. Since we forgot these, let's try to use the exact same commit message because that's what we originally intended. So, exact same status message. We pressed up on the keyboard to look at previous commands. That's how I did that. If you're not familiar with how the git bash terminal works, we're going to hit enter. Then do a git push to GitHub, master branch. And if you want to take a look at that, I'm going to go to GitHub really quick. So in my GitHub, I can see the commit messages sprint 4, stubbed in, TAUDIRT, TAUTYPE, TAUSYNC. So they're right there in all of the places that those changes are, right? So in the C11 file, we did that. In the function file, we did it. And then also in the lib folder, we did it. So we can see this commit message here. And if we click the lib folder, we'll also see the affected files. So sprint 4, and sprint 4 here. So we can see everywhere where those changes were made. Let's exit the terminal by typing exit and hitting enter. Usually you don't have to do that, nothing bad will happen. But every once in a while you have too many terminals open in the background because they didn't cleanly exit when you press the X. And then you wonder why you can't open up any more terminals, because there is a limit to how many terminals you can have open. Let's look at the agenda. Let's add the dirty flags. How are these dirty flags going to work? Well, if we remember from the diagram in TAUDEPO, let's take a look at TAUDEPO. And let's put the diagram over here. Or maybe we shouldn't do it like that because we already have this editor open. Let's close all of these and open up TAUDEPO over here. We have a 512 by 512 block of memory. And we're going to keep on subdividing it until we get a 32 by 32 block of pixels that we're going to use for uniforms. We should have a flag at this level for if this level is dirty, and then a set of... If we really wanted to be nice and clean about it, we could actually use a bit mask, because it's only 15 bits here, or 16 bits that we'll need. 16 bits here, and then this is 16 by 16, 2 by 2 cells. 16 by 16 is going to require once we get down to this level, it's 32 by 32 pixels. I say we just refresh this entire area with a texture upload, a subtext upload, where we only refresh this part of the texture. We could get more granular than that, but I think that that would be too granular at this point in time. That would be too much code, and right now, that's too detailed of an optimization, I think. I don't think we need to worry about the exact areas here that are updating. We're just going to update this entire 32 by 32 chunk. Looking at this, let's add those flags. So AAC 2020 TAUDIRT. What do we want to call it? This is a 512 by 512 section, so do we want to call it 512 for the 512 level flags? Down here, this is it's 128 by 128, yeah, correct? So this is the 128 by 128. So let's make a 128 section, or 128 by 128 flags, and there's 16 of them, right? Do we want to call it... How important is it, memory-wise? If we use an array, we're using a little bit more room, but we can also loop through it a little bit easier, and bit shifting can get a bit complicated. I think we want to use an array, just because it's the memory footprint. We're not worrying too much about the memory footprint here. It's not that much memory compared to other things, relatively. I think we should do it in whatever way is more straightforward, and we can always take advantage of the extra bits in the array slots. We don't need too much, so let's use unsigned 8-bit integers. And each of these are 16 slots, right? There are 16 index slots. Do we also want a rectangle to tell us, let's say that 5 and 11 are dirty here. We could create a rectangle like this, and then only check these slots, rather than every time going over this like that, right? Instead of 16, we could go over just 1, 2, 3, 4, 5, 6. And also, if there's only one that's dirty, then we only have to loop over 1. Is that a good optimization, or is that too much detail? I don't think it's too hard to implement. I think I want to implement that. So we could call this slots, and then we need another variable for rect. We'll call this cell, and we'll call this rec for rectangle. They'll start out all 0. And this rectangle here is not actually an array. It's actually going to be a struct. We're going to use a type def called TYP for that, and we'll figure out what that's going to be in a second here. These are to mark is the overall region here dirty? So this says, is any of this dirty, right? If any one of these subcells is dirty, then the whole thing is dirty. Then down here, we're going to do the same thing. If any of these cells in here is dirty, if any one of these cells is dirty, then we're going to mark the whole thing dirty. And that's a way where we can have the dirty flag bubble up to here. Therefore, if there is a change here, it'll be flagged here, and we'll know to dig in here and see what needs refreshing. We're gonna do it's gonna be like a quad tree kind of a structure here. It's not gonna be the most optimized way because it's gonna be good enough. So overall dirty flags, individual cell dirty flags. That's pretty good like that. We need some type of type. Now, the rectangle type here is going to have a very similar format to the type of rectangle we need for the GPU data, for the tau types. But I don't think we want to reuse the same struct, because then it's with reuse comes more ambiguity to where a certain piece of code is used. So I think we want a struct local to this file that is used as a helper for this type right here. This is the type, but it is also the variable name. I'm not sure if this should be all capital or if this should be all lowercase. However, it's all lowercase. It's going to be easier to see where it is a struct and where it's used, because when we token highlight this, it's going to match our variable name. It doesn't matter too much, but we do want to give it some consideration, and I think this name will work. Rec Inc, standing for Inclusive Rectangle. An inclusive rectangle has only 4 data points. It has the x bounds and the y bounds. Very specifically, in this order. X's first, and then y's. In a general to specific ordering. Generally, is it the X or Y axis? And then specifically, is it the left or right bound? We want to maintain a consistent ordering for this. It's going to matter. Let's create a section for dirty flag vars, and then we'll create another section for the struct. I'm not sure if there's a way to make a struct private to a file. I don't know if you can name structs as static. We're not going to worry too much about that. We're going to define type as this here. We need the struct qualifier in front of it because this is C code. That looks good to me. We're going to have to actually implement this, though, but before I do, I need to take a break. So let's start an actual timer. It should be a pretty quick break. I need to, like, microwave my tea as well. We're going to give it a 10-minute break, I think. Let me put this down here so you can see it. So if you're following along, you can also... Oh, no, did I forget the... Have I been at the wrong screen all this time? Yes, I have. So before we take a break, let's actually look at my code. And, maybe, reorganize where our chat window is here so that we don't accidentally, hide the... You know, we're hiding the preview window of what we were doing, and we didn't see anything we were doing, and that's great, because I don't know how long that was there. I don't know how long I had that screw up. So, let's review what I just did. Okay. In our dirty flags file, we have a helper rectangle that has the bounds on the X and the bounds on the Y. Lower bounds are 0, higher bounds are 1. So this is the left bound, this is the right bound, this is the top bound, and this is the bottom bound. We can make a note of that. Bound left, bound right, bound bot, make a note of why the higher bound is 1 and not 0. These here, 5, 12, and 128, if this is 1 or greater, it means this entire block is marked as dirty, and we need to drill into it and figure out which subcells are dirty. If this dirty flag here has been marked, then it means this whole thing has been marked dirty. And this whole thing may be here, or this whole thing might be here, in this cell. These flags give us a coarse overview of where we need to drill into and what we need to update. What we have here is basically a quad tree structure, but maybe it's a ox tree. I don't know. We're not really dividing everything into 4 at each level. We're actually dividing everything into 16s. So there's not really a word for that. What would 16 even be? What comes after oct? These aren't really what I'm looking for, but what is 16? Sadek? I don't know what to call it. Let's look at octa. Those aren't quite what we're looking for. Octa, yeah. So like an oct tree. We wouldn't really call it an octa tree, but let's keep that in mind when we look at 16. Oh boy, 16. Hexachideca. So technically we have a hexachideca tree. Let's go over in our notes. Technically, it would be a hexachideca tree. Does that really matter? I don't think it matters. But it's nice to know. It's a little fun thing to note. Okay. So, I need to take a break. I just wanted to go over that really quick. And let's actually get a timer going here. Make sure I can see everything. Okay, yeah, now we're actually ready to take a break. So, we're going to say, I said 10 minutes, right? I think that's enough to reheat my coffee and whatnot. Oh, still break time. So the idea is, when we use a setter, only when we use a setter, we don't have to worry about getters. But when we use a setter in TAUDEPO, we will mark the correct regions as dirty. Then, when we use GPU sync, when we use the TAUSYNC sublibrary and push up the changes to the texture memory, we will clear all of the dirty flags. If we screw this up, we're gonna see there's two things that can happen if we screw this up. One is the optimization doesn't work and we're being inefficient. And the other thing that could happen if we screw up is the dirty flags don't work correctly, and therefore we never push anything up to texture memory. Somehow we forget to set the dirty flags correctly. We don't mark the correct regions as dirty, so we push up the wrong sections of memory that were never changed. Or sometimes we push up the right memory, sometimes we don't. Or coincidentally, we push up some memory that has been changed, but was the wrong address, and then we miss some other memory that did change. There could be a whole bunch of inconsistencies to the persistence of the texture memory changes if we screw this up. Thinking about what are the consequences of this if I get this wrong. If I make a mistake, what are the typical things that we're probably going to observe as mistake? What are we going to observe if we get this wrong is kind of important, because if we can think about what the negative side effects are going to be if we screw up the code, then after we're done writing the code, if we see those behaviors that we anticipated, we'll know exactly where to fix the code right away. Now, you could say, well, just write the code right, put all your energy into writing it correctly, and then you won't have to do that. And, I mean, if you're an infallible person who never made any mistakes, then yeah, sure. But you're not. And even if you are, somebody else might not be. Somebody might touch the code and screw it up, and you might want to have the experience to understand what's probably going on based on looking at these symptoms. Alright, break time is almost over. Alright, break time's over. Let's get to it. This looks pretty good to me. We need to also have the define for int32. And we can keep it as int32. The other inclusive rectangle will need to be unsigned integers. But for this, we could actually keep it as int32. But on second thought, we have these dirty flags here already. And with these dirty flags, here that mark the entire region dirty, we know that if the dirty flag here isn't set, that we can disregard whatever data is in here. And then we don't have to, with an integer, we could make these in an invalid range to say that we shouldn't use them. But we already have these flags, so that would be some extra computation that doesn't need to be done. And I think even though this is not going to be used in our texture memory, it's going to be used to check updating the texture memory, but it's not going to be used to encode anything on the texture memory, we should probably use unsigned 32-bit anyways, because we're going to have a very similar, almost identical struct for one of our tau types. And we might as well just code it the same, and that way when we're looking at it, we can be like, oh, we've seen something like this before, and know what to do. So define U32. We're going to define it as a U32, all the members. That looks good. Now let's make sure this actually compiles, right? Maybe we made some mistakes somewhere. Doesn't look like it. Okay. Let's go to git bash here. Okay, the next step. What are we doing next? Well, we've added those flags. We should actually probably use them somewhere, right? Since we've just added this, where are we going to use that? Let's go use it. So in the TAUDEPO, right here, in the functions themselves, we have getters and setters, right? And we do not care about the getter. We only care about the putter. The putter is the thing that's going to dirty our data. Reading the data is not going to dirty our GPU, CPU synchronization. Let's look at the getter. The getter has enumerations that identify both the variable and also identify physically where that variable is in memory. Let's open up TAUDEPO's data over here so we can see this. So the 0 to 15 here corresponds to this. The 0 to 15 here corresponds to this subdivision here. And then finally, the 0 to 255 corresponds to this 32 by 32 pixel block of memory that we're going to group into chunks of 4 pixels each to get a total of 16 by 16 cells, where 16 by 16 equals 256. Therefore, 0 to 255 values. Now, we might want to make a note here that 16 times 16, what that equals, you know, because maybe I'm full of shit and my math is wrong, right? So let's make some reference here for what these values actually are. Because, you know, I'm not the, you know, I know my power is a 2, but, you know, I don't know, but 16 by 16 is not one of my powers of 2 that I know. And maybe I should get better at my power of 2 and know, like, I guess these aren't really, these are more like squares. Like, I know my powers of 2, but I don't know my squares, I guess. So maybe I should learn my squares as well. But you know, I learned my powers of 2 not by trying to, like, memorize them every day, right? I learned them because I use them a lot. And I think that's the way to do it, right? If I eventually, you know, use squares so often that I have them memorized, then I have them memorized because my brain knows that I need to use them a lot, right? So 32 by 32, 32 times 32 is, what is that? 1024. And now we can think about this for a second. 1024 means we're going to take 10,024 pixels and we're going to upload those. And that's our minimum granularity. That's actually a little bit... I'm not quite happy with that. That actually seems like way too much. It seems a little bit way too wasteful. I know I said I didn't want to get that granular, but now that I'm actually looking at the actual numbers and I'm like, whoa, that's the equivalent of every frame pushing 1,024 uniforms every frame. If every uniform is just a float 32 or an int 32 or whatever. That to me is way too much. Way too much data going across our pipeline. I don't wanna do that. I think we should actually have some dirty flags at this level. And we know that this is a 16 by 16 grid here, right? Because we're going to take, each cell is 2 by 2 pixels, and this memory region is 32 by 32 pixels, but the actual segmentation is 16 by 16 groupings because there's going to be 16 by 16 of these kind of cells here. So that's kind of like how we're chopping it up. So since we know it's 16 by 16, well, the way we've kind of classified these is 512 by 512 is the entire memory region size, and 120 by 8 by 128, these are actually the sizes in pixels of what we're dealing with, right? How many pixels are we dealing with on each axis? If we want to keep that, then this is a 32 by 32 section. Therefore, we should do the same thing with our convention and just be consistent, right? Be consistent. So we're going to go 0, 3, 2. Right, we want to keep the spacing identical, just because we're OCD like that. And the 0, 3, 2 is not 16 cells, is it? Or do we also divide that into 16? And we see 16 by 16, 2 by 2 cells. Really? So it just works that way, huh? Oh, it's 16 by 16, not 4 by 4. So this is 16 cells here. 16 total cells, right? This is a 4 by 4 cells. 4 by 4. And here is 4 by 4 cells. But here is a 16 by 16, which is 256 cells, or 255. It's 16 by 16 cells, correct? And if it's 16 by 16 cells, then we need much more than just 16 slots here, correct? Checking our calculator, let's do a 16 times 16, which is going to be half of 1024. 16 times 16 is 256. So we know that this needs to be 256. So that's a lot of data. That's, but I guess it's good that we didn't decide to do a bit flag for this, because even though these two things can have a bit flag, because you can put it in an unsigned 32-bit or even unsigned 16-bit and use 16-bit flags, this cannot, right? There's no such thing as a 256-bit integer. Well, at least not right now. I'm sure on some very advanced types of supercomputers, you probably do have some type of 256. I don't know. Maybe it will be a thing in the future, but right now it's not. And we want our data to be as homogeneous as possible. So this should be homogeneous, this should be homogeneous, and this should be homogeneous. That looks good to me, how that is. Okay, now that we have that, let's look at what we're doing here. What do we need to do? Let's undo that for a second. Let's add a section here. So we're going to add a section called Dirty Sector Management. And all of the logic that has to do with TAUDIRT will go in here. First of all, anytime we do a footer, the top level is always dirty if we set at the top level. For the hold on here. If something here is dirty, then something here and something here is dirty, right? Is there any benefit to having all these different dirty flags? Or I see. So on the top level, it's just dirty or it's not dirty. However, on the lower level, we can have up to... Well, these are the dirty flags for... Is this are these subcells dirty? Are these subcells dirty? Are these subcells dirty? Right? But if... So I don't think we need any dirty flags for... I don't think we need to group it like this. I think that all we need is one dirty flag for the whole thing. Because these are going to manage the granularity aspect. So... We'll call it dir any for dirty any. Equals 0. Is anything at all dirty? Right, so it's going to be like an overall, overarching kind of thing. And do we really want to name it like that? We don't need the 512. We can just call it dir any for dirty any. And might not be the best name, but let's just stick with that. Once we've decided that this is dirty, we can use each one of these to flag the appropriate cells that are dirty. So the first subcell, mark that as dirty. Within that division, mark the next subcell as dirty. And then finally, the last subcell here, we're going to mark as dirty. Okay. We also want to expand all of our dirty rectangles. In order to appropriately expand our dirty rectangular selections, we need to make sure we know whether or not the rectangle is valid in the first place. Because if this is the first time that the rectangular segment has been used because it wasn't dirty before, then we can't expand it, correct? We can't expand it from anything because it has no valid origin yet. So, let's do the operations for each rectangular selection. So if this current cell is so this is going to get a little bit, we're going to take these and we're going to make some defines so that, now it is a little bit cluttered here already. We're only going to use these defines in the dirty sector management. So we could take them and put them right here and create some defines. So define, and all we're going to do is we're going to take the, now, oh, that's interesting. So if we want to take these and make them defines with minimal mental indirection, well, we can't because these are starting with numbers and they're not valid identifiers. So maybe we should rename these out of convenience and put the size at the very end. And also, that seems to be more of a general specific ordering anyways, because rectangle and then the size, right? Now, maybe it's a little bit arbitrary deciding which one goes where, but since we want to make these defines and shorten what the names are, we should order it this way. That way, we can easily do that without running into any trouble. Looking at that, we see dir whatever, and we see dir any. So that is actually the better ordering, right? Because dir any basically means any of these block sizes. So this is a more consistent naming convention here anyways. Taking those, we can paste these here and take the smaller section here, and we can paste it there, and now we have a shorter alias for these, right? So instead of having to type all this out, we can type these here. And we can do the same for the other names as well. And it is going to get kind of bloated here, but don't be afraid of having long function names. We're going to need the same for this, lastly. And it seems that I have forgotten the namespace here. We'll take these right here. These will be our shorthand identifiers. We'll paste them there. So that's quite a lot of stuff. And we also forgot the any flag. Or this kind of flag just hanging out here. And also, these don't actually exist right now. We can maybe comment those out. I don't know. Maybe we want to just keep that for reference, just in case. Or maybe we're just overly bloating our code doing that. I don't know. Okay. So, with all these kind of in place, we also want to take this, and then down here in this section, we are going to Please don't. Okay. Sorry. What? Sorry.
I just came down here to be like, hey, finish my exam. I want food. You want
Good
food?
job.
You want steak?
No, I wanna work.
Well, okay. I
Okay.
will leave you alone. Are you streaming?
Yes.
You're a pissy pants. Now it's immortalized.
Okay.
Alright, goodbye.
Alright. So, now that I have these defines here, we're going to undef them. And we're going to keep the alignment as well. Two spaces between the keyword undef and what we're undefining. So the block up here aligns with the block up here. We're going to create a checksum of what's here, since there is quite a lot of things here. And it would be good to just know, well, how many things do we have here? Okay, so it looks like we got 10 things. And then up here, we also should have 10 things as well. Some of those things are commented out, but the thing is that I'm not certain if we should put them back in later or how we're going to do that. So we'll just keep them there for now for reference in case we actually decide to use them. Okay. So we got a lot of stuff here, and that makes this section kind of like very bloated, and that kind of sucks. But it's going to help us focus on what we're actually doing and keep our column limits kind of nice and small here. So now we can keep it like this. And we need to, before flagging this is when we need to look at our rectangular regions. So with the so this index here, do we have a shorthand for these indexes? Doesn't look like it. Let's see if these are used anywhere else in our code as a single variable, or if we can use these as defines. So looking through this, it looks like we can use these as defines. And we're going to use them as a define yeah, why not right here? This is where it's going to be used, so let's define it here. So, tau015, we're going to get rid of the extraneous pieces of this. The commonalities, dex and 000, right, because the beginning range is 0 and the ending range is 15. We want to get rid of some of that redundancy and make it a little bit more terse. And actually, we could get so terse that we omit the range as well. We could omit the range as well, but it might be valid. It might be valid to see the range in here. So when we're using index accessors, we can notice that. Take note of that range. We're going to undef this down here. And actually, before we undef it, why don't we make the comments here that need to be made? (11, 12, and 13). And we can copy this and just paste it down here. 11, 12, and 13, and then we can just write undef here. Space that out. Okay, now that we have all of our shorthand established, we're in a good position to start writing the actual logic. Finally. So in our 512 by 512 cells here, so the cell 512, oh, and that's also right. The reason why we did this was so that, you know, when we make the shorthand, we can actually use it as an identifier because we're, well, actually, maybe, I'm not quite sure. Maybe we could use macros that start with a number. I'm not sure. I would like to avoid it. I think that's just a bad practice anyways. So in these different tables, for the different memory regions, we can use the different... Now, you know what? If the memory region doesn't need to be shortened, I think that maybe we shouldn't. So if we have enough room, I think maybe we shouldn't shorten it. I don't know. But over here, we do need to shorten it. I'm not sure about what would be the best way to approach this. What type of consistency would be most important. But let's look at if cell 512, the 512 by 512 outer region, denoted by the tau, right? It's the tau cell. The tau cell that's currently in focus. If that is all already dirty, if it's already dirty, we're going to want to expand it. And there should only be two choices here. If we want to keep this nice and aligned, we could write it like this, which is kind of weird. And people might not like that we're like changing our style, since that's not the way I usually do it. So I do like that if we have it like this, we kind of have like, it's more symmetrical in that aspect. However, then things don't line up correctly, and we would really need to, you know, space it out like this to get the correct alignment, and people might look at that and be like, oh, that's weird. You know what, we're not going to worry about if it looks weird. We have a whole bunch of inconsistencies in our code, but our formatting standard isn't meant to be something that can be algorithmically done by a computer, right? It's supposed to be something that takes a human eye and is done on a case-by-case basis. So I think this makes sense to me. So this is already dirty. Okay. So this is already dirty, and this is the first time. Now, if it's the first time that it's dirty, then we want to take this cell here, right? And this cell number is whatever this cell number is. We need to find the X and Y, and we want to mark it in this rectangle structure. Let's convert index to xy, and convert the different cell values into their appropriate x and y's, because we're going to need x and y locations for these 3 different dirty rectangular regions. Now, the memory region is 512 by 512 pixels, but the actual grid we're on is a 16 by 16, and so the width is 16 cells. So we might want to make a note of what these numbers are, so we're not confused. The TX and TY, we're going to need one for each one of these levels, so we're going to need a way to identify where we are in the hierarchy here. I'm thinking one way we could do it to keep these variables relatively shorthand is we could say that the x0 is the first level. And then as we go deeper and deeper in our nesting levels, we will increment the number. And we don't want to mistake these numbers, these x0s, y0s, for these ones here. So it might be a bad choice. We might also want to call it, we could call it x, a, b, and c. We could do that as well. I think maybe that would be better. Now, I tend to steer away from alphabetical order just because I'm not as good with alphabetical order as I am with I'm much better at numbering than I am alphabetical order. I think alphabetical order is just not as ingrained in my head as numbers. And I think that's probably true for most people. So this 128, these 128 by 128 cells are, well, 128 pixels. Because we divided into 6, because we divided it 4 and 4 on each axis. Yeah, because we sliced it. We sliced it into fourths, right? We sliced, earlier up we have 16 by 16 cells, which means that's 4 by 4. 4 by 4. And because we take this 512 and we cut it into 4 by 4, that means we end up with a whole bunch of 128s down here. And because this is also 16 cells, this is also a 4 by 4 as well, and we should make note of that. Because it's still 16 cells, because it's still a 4 by 4, the math will still be using 16 as the width of the data. Now for C, we're going to take 0, 0, 3, 2. Right, the index is from... the index never hits 32. These are the memory sizes. And the 32 segment is, what, 16 by 16? 16 by 16 cells. And 16 by 16 is 256. So the index can go up to 256. So you know, is this the best name? Cell 32. Well, it's the size of the memory in pixels. And we want to be consistent with what we're naming it. So let's just stick with that, and we know that this needs to be 256 and 256. And this is 32 pixels. 512 pixels, 32 pixels, 128 pixels. But it is 256 cells. Is that 256 cells? Yes, 256 cells, because each one of them represents a data point. 256 cells. It does look kind of weird, because we have 16, 16, and then all of a sudden we got 256. .512 by 512. Let's make a note of what these all are. 128 by 128 pixels, and it's 16 by 16 cells. Actually, it's 4 by 4 cells. So that way, when we're looking at some of these magic numbers in the code, we can look at the comments and see where those are coming from. This here, the last one, is 32 by 32 pixels. And it is 256. Now, how do we get 256? It's not 256 by 256 cells. It's 16 by 16, right? So it is a bigger number, 16 by 16. And 16 by 16 is 256 cells. Now that we have all of that kind of partitioned out, we could try to make it a little bit more normalized. So we could put some leading zeros in front of this, which obviously looks a little bit awkward. But by doing that, we can get everything to line up a little bit nicer. And it's going to be easier to see the patterns. Except if you look at it and you're like, well, that looks like octal notation, then you might be a little bit kind of like, why did they do this? So let's look at these numbers here. 16 cells, 4 by 4. So these comments here can be removed. And for clarity, if we remove the comments, and we have the comments up here, I think that reads a lot better. I think that is much clearer in terms of just looking at the code and understanding it. Let's align these so that they all kind of match up. So we just want the 1s, 10s, and 100 places to be aligned on all of those. 16 cells, and 256 cells. And for each number of cells, we want to use the modulus and division to match the number of cells, which we are doing. X, X, X. So the X is whatever the remainder is, correct? Yes, X is the remainder, and then Y is how many full rows of data we can get. Get cell indexes. So here we're just getting the dirty tile locations. That is what we will call this. And we can subdivide this section and use a less bold divider, right? We're using a capital here, we can use a lowercase here, and kind of communicate a little bit better that this section here is a subsection of a larger section, and have an idea of how far down we're nested. Note that we have 1, 2, 3 levels of indentation, yet we're only inside of one scope, right? We're excessively indenting to give more categorization than scope alone would give us. That looks good to me. In here, if it's already dirty, we want to just expand the current values for these dirty markers. We have these rectangles. We should probably keep... Do we already have the enums for these rectangles? Yes, we have the enums for these rectangles. If it's already dirty, we're going to do... We're going to create a macro for min. And we only have to compare the mins and the maxes, because the minimum boundaries and the maximum boundaries should be correctly ordered. And it's already dirty, so we only have to widen the rectangle on up to 2 boundaries, one being an x boundary and one being a y boundary. Let's duplicate this and do the same thing for our y boundaries. Do we want to do that, or do we want to do all x's first? Thinking about it, let's do the x's first. The reason for that is we want to keep the kind of ordering that we're going to use when we pack this onto the texture, and the ordering is going to be from the struct is x's and then y's. So we should keep this ordering here when we're writing out our functions. When we're writing out our logic, right? Taking this to expand it, looking at the y's now, and this should be a y. So we have the x's, the y's, and both of them are a's. And we can see them up there. For the lower boundaries, we're going to use min, and for the upper boundaries, we want to use max. If it's the first time that it has been marked dirty, then all of these are just going to be set to exactly that tile. So rather than min and max, it is literally just this. We can line it up so that we can see the pattern between the blocks, right? So we can see the exact same spacing, and we can see the XA and the YA right here, right? But there is no min-max, because we're not going to compare the previous value that was in the rectangle, because it's the first time it's dirty. Whatever those values were obsolete and not relevant at all. So we're not going to use them. We're just going to set without any min-max comparison. For the other sections of cells, it's the exact same procedure. So for cell 128 and cell 32, we do the exact same thing. So we should dirty sector management. This section here is expanding the rectangles. Expand dirty rect selections. So we'll expand dirty rect selections. I think that is a good enough section name here. And we should mark that as well. We should give it a little section to explain what's going on here, because our sections do get kind of long. Some people would advise that if you're gonna name stuff like this, that it should just go on its own function. And I disagree with that, because this is the only place we're gonna do this logic, and we should not put something in a different function if we're not gonna actually reuse that function anywhere. Because we're just gonna multiply our surface code, we're going to multiply the surface area of our code for no extra added benefit. Now, if we want this section here, we really should indent one more time. And then we kind of lose the ability to add that marker. We could do... I don't know what we could do. We're really running out of room if we do that. And... we could make a little key here, up above. Let's make a little key right here, less than or equal to 0. Okay, so this is just a little summary of what's going on here. If we see a greater than or equal to 1, it means the rectangle is valid and use min plus max. And if we see less than or equal to 0, then the rectangle is junk and we need to reinitialize. And we might be able to kind of squeeze something in here. Okay, so we have, like, just enough room to... We should use the same kind of tag. And we have valid and junk. So we can do a little at here, at valid and at junk. Maybe we want to align that, so maybe we'll just do, like, an at junk. And that identifies the section. We got a pretty nice section here. We want to duplicate this multiple times and replace the proper variables. Now it is pretty thick here, so we might want to add some type of section header here. We could name it after the diagram in the code. And when we see this hashtag, we can see what diagram that corresponds to. Similarly, What diagram does this correspond to? And because we already used this kind of notation here to mark the top and bottom of the sections, we will use markers that tell us what the section below is, but they don't tell us where this below ends. And I tend not to do this kind of notation where we're only marking the top of the region, but we never mark the end of the region. We kind of have to infer where that's happening. However, we've already done this enough, and we're running out of space, so we need to change the convention a little bit to get some type of clean dividers that aren't too clunky. So this last section here is diagram var cell, and we can take that diagram, and now we have different sections. And we can highlight them to make absolutely sure that we have 3 unique colors. And yes, we have 3 unique colors. We've got cyan, orange, and yellow. Now we need to replace the letters. So B's and C's, right? Alphabetical order. After we've replaced the letters, we have to look at it again and be like, that was totally wrong, fix it. B, C. Now, a lot of this stuff that you're looking at, you're like, this is very repetitive. Why not just put it in a loop, right? Why not figure out how to put it in a loop? Well, if we tried to put it in a loop, we would have to add extra abstraction. We would have to look at all of this kind of stuff here, and we would have to create some type of generic container that has this kind of data in it, which would be kind of hard because this is 256 and these are 16. And then even after we managed to make that generic container, all we've achieved is shortening this code and making it more abstract, and making it harder to follow. The code is now harder to follow, and we've saved some lines of code. So it was extra effort to write that extra code, and what you've effectively done is compressed your code. You've just manually compressed your code. That's all you've done, and now it's harder to follow because a looping structure is more mental work to figure out what's happening, because you have to mentally expand the loop into what it is, and this is already the contents of a loop that's going over 3 structures. It's a loop of 3 things, but it's expanded. And this is much more straightforward. Now, there is the potential for mistakes, right? Because now we have to meticulously make sure that all of these are correct. But it also adds extra redundancy to where we can compare this against this and see what's wrong, because they should look almost identical to each other. And you can also kind of see the patterns a little bit better, because you can compare the blocks directly and see what the differences are. So these rectangles, this rectangle here is Rec 128, correct? Yeah, Rec 128 is here. So we need to change the numbers here. And then after we change all the numbers here, we have to change the numbers on the final rectangle. And the final rectangle is Rec 032 for a 32 by 32. So right here. And after we manually do all this replacement, we'll do some double checking to make absolutely sure that all of these have been correctly refactored and that everything is correctly balanced. Because since we're being so meticulous about how all this all goes together, if we highlight everything, it should be obvious if we screwed anything up. First thing we'll do is we'll do the 512, the 128, and the 32. And we notice every section here has a unique color. We didn't accidentally interlace any of those, and that's good. The next thing we want to do is, let's say we're going to use, like, I believe a purple and a green for the, oh, that's for X0 and X1. So X0 and X1s, we see them, they should be clustered at the top of each of these sections here. And that's what we see. Let's use, I don't know, we only have so many colors at our fingertips here. let's use, I don't know, 3 and 4. I really don't know. Let's not worry about it too much. So these are our Y's. And looking at our Y's seem to be correct as well. There's the zeros first and the 1s second. The Y's are the second partition here. That looks pretty consistent to me as well. Doesn't look like we made any mistake there. But I just realized somewhere where we did make a mistake, right here. We made a mistake. So we can address that right now. So tau 015 is the input, correct? Yes, it is the dex tau 0015, which is these things here. So it's tau sub and var. Tau sub right? Because sub and sub, tau cell, tau. Lastly, we have var, var cell. Therefore, these should say var, and the var is 0 to 255, correct? If we go up here, we can see the range, and the variable name is 0 to 255, yes. So lastly, in the var cell, we want to do var 255, and we also have to look it up in the correct location as well. Var and 255. So these cells here, this shouldn't be cell 512. This should be cell 032. Cell 032 and var 255. If we look at cell 032 here, we see that it has 256 elements, so we know we're not going to go out of bounds here because the name of this variable says it goes up to 255. So we've chosen the correct terse names because with these terse names, we can see if there's a mistake just by looking at the names. The names themselves will tell us if we made a mistake. Though maybe you might say, well, maybe this should be called cell 255 rather than cell 032. The idea behind that was we already have the 256 here, therefore giving this a different name here would help with getting the most information out of the shortest possible line, keeping the lines short but also having them very information dense. And so that's why I chose the names I chose. Right? Also, you see that if we tried to use this number here, well, these are both 16, so that wouldn't have worked anyways for consistency. Let's look at the cell here. So the subcell, 128, we need cell 128 right here, cell 128 and cell 128. Within here, is it sub? Yeah, tau, sub, and var. Let's clear out our color coding and make sure that we can get some unique colors if we color this, and we color this, and then we color this and color this to match, and then finally we color this and we color this to match, that we have unique sectors. Unique, and I see a mistake here. This should be labeled after the array. It looks like we're labeling it after the array. And that's fine. It just needs to be a unique error message, but we should be consistent in how we're doing it. And since we are using the cell variable, we'll use cell 128 here in this error message, and cell 032 in this error message. Let's do it over again. So every time we find a mistake, we want to do the whole process over again. and check one more time. And we're going to keep on doing that until we've done our check, we've done our rounds, and we don't actually see any mistakes. And if we can do it like that, then we'll be fairly certain that we are good to go. Let's highlight the X's and the Y's. The X's and the Y's. And the X's and the Y's. Now that we've token highlighted these, we can look at other portions of the code and make sure that we have the 3 identifiers in that same order in places we expect them. I see cell and tau, right? There are 2. We're using 2 tokens. That makes sense to me. There's no highlighting here because, right, we split this up. We took the tau part and the number part, whereas here we took these 2 parts. That's why we have nothing highlighted here. But we want to pay attention to this and that. Let's go up and look at what the other code looks like. So we have our 3 blocks of memory here in the first group of defines here, and then below here, these are the index accessors, and those look the correct color. Cyan, orange, and yellow. So this is in the correct order. The 512 matches this 512, the 128 matches this 128, and the 32s match each other. Let's look at these numbers and compare it to the numbers over here. We see 16, 16, and 256, and we see 16, 16, and 256. So that is good as well. This is a 4x4 split of the memory. The memory regions being 512 by 512 and 128 by 128 pixels each, for a total of 16 cells. The cells are different sizes, of course. This is the X. Where's the Y? The Y is right here. Let's double check that. We have X. Here's the different X's. XA. Okay, let's look to make sure there's a consistent pattern with the Y's as well. So the Y is just in... The different Y's are just in one place, correct? Yes, and that makes sense because the Y is the whole amount that's left. Also, let's fix that. This was originally the snippet I used was originally for Golang, not C. That's why I had the colon assignment like that. But the general formula is still good. That looks good to me. So the idea here is when we set a certain, let's say we set this variable here. It marks this cell as dirty, and it also expands a dirty rectangle to fill this section. And then later, if we set something here, the dirty rectangle will expand to fill all of this. So the dirty rectangle kind of expands to accommodate the bounds of all the data that has been set within here. It's a kind of a heuristic where it's not perfect, right? If you set a variable here and you set a variable over here, then the dirty rectangle has to expand to cover it all, and you're going to update some values that were never changed. So it's not perfect. However, the alternative to just scan through all 1024 options and then only update the options that have changed, that's a trade-off. You're going to use more CPU power, but you're going to use less GPU bandwidth. And that might be the correct solution. That might be a better solution. You'd really have to profile to find out. So I don't know if we're, maybe we're over-optimizing this, but we have a good balance here. We're not too CPU heavy, and we're not too GPU heavy either. So I like the decision we've made, and I'm going to stick with it. Let's look at our sections here. We have dirty sector management. And down here, dirty sector management. We have 13 defines here, and we have 13 defines here. We are missing something, though. We have a min and max function. How do we want to do that? Do we want to make a min and max function in TAUDIRT? I would say that that's probably the best place to do it, because this logic here is just for dirty rectangles, and even though TAUDIRT is supposed to be a data-only class, having some helper functions in it kind of makes sense. Having the helper functions in the... that would be the logical place where these helper functions would live, I think. Yeah, so let's do that. Let's go into TAUDIRT. This is a really simple helper function. It's a very simple helper function, and it could be used by other libraries as well. It's something is in the... it could fit the category of a general utility function. However, my experience is that when you make generic utility functions, you just end up with this file that's bloated with a ton of functions, and you start to lose track of those generic utility functions. And since the generic utility functions are so simple, I think it makes more sense to duplicate the code and have them closer to where they're used. Because then when I see these utility functions in here, I know exactly where they're being used. Whereas, what'll happen if you're making a generic utility file is they tend not to be, the generic utility functions tend not to be reused as much as you think they're going to be reused. So, you end up with this, like, oddball collection of random functions, and just by looking at the file, you can't tell where the hell different things are used. Yeah, you can look it up and figure out where they're used, but it doesn't seem like a worthwhile way to organize code to me. I don't think putting a whole bunch of miscellaneous utilities in a single file is a good idea. In fact, it almost can turn into what I would call a God object. A God object being just a big file that just does everything, right? A generic utility is going to have, by its very nature, a whole bunch of unrelated behaviors in it. Unrelated behaviors for unrelated systems, and the only thing that binds them all together is that, oh, they're all little tiny helper functions. That is not a good categorization. Now, if you asked me this question a year ago, or I would probably have a different opinion. I'd be like, oh yeah, generic utility. But you know what? I've done this so many times. So many times I've made generic libraries for like generic little helper functions. I've done this many times. Like, for over 10 years I've done that. And it's never helped me. It's always just added more confusion to my code. So none of this generic helper shit. It's not a good idea. That's my experience. That's what we're gonna go with. And remember, we're not gonna worry about, oh my god, we could have reused this and now the memory footprint of our executable is larger. We're not gonna... We got plenty of memory. The computers and technology, right, they're gonna get faster without any change to the code. Every year we come out with faster machines with more memory. That aspect is going to improve no matter what. So we shouldn't worry too much about optimizing that. We don't want to abuse it. We don't want to grossly over-abuse our memory footprint. But we don't want to make things more difficult on us programming-wise because we're trying to micro-optimize things that'll just naturally get optimized with time without any effort on our part. Also, since we have this helper and it's for a very specific case, for a very specific class, we can look at the values we're using. We have these integers that have a range 0 to 255. And if we look at our cell size, we got 4 by 4 cells and we got 16 by 16 cells. And that's plenty, so 255, 0 to 255 is plenty to fit these numbers. We got plenty of space, right? Because we only need the digits 0, 1, 2, 3, and 4 for the 4 by 4. Actually, no, we just need digits 0 to 3. We don't count the last index. And then the digits 0 to 15 here. This size is good. We could use a... No, we can't use a smaller size. This is as small as we get. There's no U4 for 4 bits. Well, there might be, but let's not use odd, archaic types. I think 32-bit, 8-bit, and sometimes 64-bit is what we want to work with. We don't want to work with, say, we don't want to work with like 16-bit. We want to just... we don't want to fractionate our variable types too much. We want to be kind of coarse with that. But with the min-max helper, since we know these values are... Well, actually, let's look at this type here. This is a U32. Should that be a U32? Because we know that... We know specifically that what the bounds are here. And this U32 is not going to be persisted on the GPU memory. In fact, since it's not going to be persisted on the GPU memory, I think I would rather choose this. This rectangle is not okay, making a note and making the not very bold. This rectangle is not persisted on GPU memory. Make a note of what the implication of that is. Say that's much more homogeneous. This whole file only uses 8-bit integers, unsigned 8-bit integers. I do like that. That looks good to me, and we don't need that extra room anyways. So like I said, if it's not too much trouble, then we can optimize for memory footprint. But as long as we're not completely abusing the memory footprint, if it just makes the code easier to use by abusing our memory footprint, then we're going to abuse our memory footprint. Well, I don't want to say abuse. Any gross abuse of the memory footprint would be a bad idea. But if it's not a gross abuse of our memory footprint, we just want whatever is easiest to use, whatever's easiest to read. We'll name it after the file that it belongs in. And because we're only using it in one place, what we can also do is we can name it... This is old and this is new. Right? When we're looking at the min and max, the way we have organized this code is we have the old value on the left and the new value on the right. So bow new and bow old for boundary old and new. And really simple, basic kind of stuff here. If we want this to be as readable as possible, so U08 bow min let's give this a look here and see what's going on. We have the old and the new boundaries. We'll start off by saying that the minimum boundary is the old one. And then we'll say, well, if the new boundary is less than the old boundary, then the minimum is actually the new boundary. I think that's a little bit confusing to read. This is indented kind of wonky, but I don't want to flip these signs. Mentally, to comprehend this, old less than new. If old is less than new, then the minimum is going to be that old. And then same thing for here. If the bow new is less than bow old, then the minimum is the new. So these two identical things are stacked on top of each other. And these are flipped, correct? These colors are flipped here. So up here, we're just kind of flipping it. Do we like that, or is that bad? Is that ugly? That's okay. I like that. Let's keep it like that. There's some extra processing power involved with this. This is not the most efficient way to write this. But looking at it, I think it is the clearest way to write what we're going for here. This min here, we could space this out here, so we can see the min and the min. And we can also, all those mins kind of line up nicely, and that's nice as well. If we're also thinking about that, we could line this up as well. And that's what I'm talking about, that the formatting doesn't really follow a rule that an automated processor could use, because when I'm doing this, I'm looking at the code holistically. And it's going to annoy the hell out of a lot of people, I know. But I want to be able to see associations kind of quickly. So I can see the old here, and then I can see the new here. I can see that new, new, and old. So there's already, interesting patterns emerging. And when I look at these patterns, I can automatically tell if something is wrong. For instance, we can do a quick checksum here to be like new, 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 new. There's 4 news, but then why is there 1, 2, 3, 4? Oh, yep. So 4 news, 4 olds. I just thought that count looked off. Also here we see 4 as well. So everything has a checksum of 4. And by having the ability to just checksum it like that, we don't have to think too hard about whether it's correct or not. We can see the patterns in the code, the visual aesthetic patterns, and use that as a heuristic to validate the code. For this, change the name to max. Let's highlight min, because min needs to be changed to max. For max, all we need to do is flip the sign here. If bow old is greater than the new boundary, then we're going to stick with old because that is the highest value. If the new is greater than the old, then we're going to stick with the new for the boundary. Dead simple. Keep it simple, stupid, right? Now the idea here for why we did this is because even though it's simple, it's a relatively large chunk of code when we think about how many times we got to use it here and here. And this is what I'm talking about. We have these sections 1, 2, and 3, which are almost identical. But we're not going to shove this into its own function because it's only going to be called from one place. However, here, well, I guess this is technically only called from one place, but you can see the large frequency at which it's used, that expanding it in all these places, it would just be ridiculous. Once again, it's kind of an art form to how you make your decisions here, and there's not one hard, fast rule for how to do things. Even though sometimes it might, like, I'm probably a hypocrite, and, well, I know I'm a hypocrite, right? Everyone's a hypocrite, because we're not machines, we're human beings, and we're capable of fuzzy logic. Also, human beings tend to have, like, a lot of constraints applied to them, so once you have enough constraints applied to you, some of those constraints inevitably conflict, and you have to not, crash your mental software because you have contradictions. So these min and max functions look like they're going to work to me. Do want to do one more little pass through, make sure that everything looks correct. I mean, all we need is this greater than or equal than. We can double check, make sure that we have less than for min, greater than for... We can make sure that all the colors are the same, because everything should be analogous between these two functions. And that's why I put the min-max helper into its own section divider, because the functions are so similar that it makes sense to group them together like this and give it kind of a little dash divider. The dash divider is a soft divider that tells me that even though it's a division, something about the things being divided is similar enough that you could count them as one thing. That's kind of what I'm communicating with a dashed line, or I'm trying to communicate visually. With these U08s, we actually have to define those. So define U08, and down here, undef U08. Oh, undef. Do I not have an undef for this? Looks like I don't have an undef for that. Let's add an undef. In our shortcuts over here, let's write undef U08 and U08 undef. Also maybe like undef and U08, U08 undef, and then UO8 undef UO8. Actually, we can't say undef 8 because that could mean signed or unsigned if we say undef 8. So that is too shorthanded. Then here we're gonna do a sorry, I don't need to, gotta not use those filler words. Undef space UO8. My shortcut script doesn't allow for a hashtag like that to be in the shortcuts. Therefore, I'm very familiar with the escape code for this. In Unicode, it's U plus 0023. I believe the leading zeros are optional. But the syntax is, I don't know where this syntax comes from, but this is the syntax that AutoHotkey uses for Unicode escape sequences. U plus for Unicode, I don't know why there's these curly braces, but I've seen it in other documentation as well. Therefore, I know it's not unique to AutoHotkey. We'll keep it like that, and if we want to search through our shortcuts to find this, we might not be expecting this, so we keep this copy here for reference. We could also do this, put it in there like that. That's enough redundancy for me, where I'm confident about having it in there. We're not going to reload our shortcuts, though. That's just for the future. Next session of programming we do, we'll have that at our fingertips. For now, we'll have to just write it by hand, which is not a problem. It's just a few keystrokes. Now, a lot of the stuff you see me do takes a lot of time. And you might be like, why are you taking all this time to do this shortcut stuff when it seems like you spend more time doing your shortcuts than you do actually using your shortcuts, right? My analogy for that would be, let's say you're in a kitchen and you're like cutting tomatoes, chop, 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 and you got a really sharp knife, chop, 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 and you're being really fast, you're zooming through your work. And day by day, you keep on doing it, you zoom through your work, and your knife is super sharp, and everything goes really fast. But day by day, your knife gets duller, and duller, and duller, and duller. And eventually, you try to chop those tomatoes, and it just squashes in half, and it's a mess. And you gotta, like, use this one part of the blade that's still sharp, and you gotta, like, slowly saw. And so your efficiency just slowly diminishes until it's completely horrible. Therefore, the way I try to manage that, I don't know if therefore is the correct transitional phrase. The way I try to manage that is I'm adding these shortcuts and doing all this maintenance, and that's the equivalent of sharpening my tools. I'm always sharpening my tools. In calculus, I'm sure we could derive some type of algorithm for a general heuristic of how often you should be sharpening your tools. Because I'm sure there's a more optimal way to do it than the way I do it. But when it comes down to it, having my tools up to date is more of a priority than going fast in the moment. When I keep my shortcuts up to date like this, I can... Going fast is more like an emergency thing that I do every once in a while, where it's like I just need to go really fast, and I got all these shortcuts at my fingertips so I can go, 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 go. And because I've been maintaining my shortcuts, because I've been keeping my knife super sharp every fucking day, when some type of emergency hits and I gotta like go, 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 I'm ready to go. Right? It'd be like if you always fill up your gas tank before you get home, and then one day you gotta like speed out of the state for some reason. I don't know why, some type of weird emergency. Your gas tank is already full, you're already ready to go. Now, how important is that to be ready for something like that? I don't know if it's that important. It really depends on what kind of situation you're in. And right now I'm not in that kind of situation where that's that important, but I have been in that kind of situation before. Let's get rid of some of this extra spacing here. I don't think we need it, because we still have this kind of like double spaced kind of spacing here. We could even remove this, and I think we would still be readable. I think that is still good. We could also get rid of this, but I tend to like to leave a little space between these section dividers here. Going into where we're using this, we need to well, here's where min and max is used. Do we want to just add the define there? We already have a large chunk of min and max of defines here. And we do want our macros to be close to where they're used, especially when they don't have the word macro in them, like this min and max. Therefore, I think this is a good place. Min and max, and min and max. The downside of this is then we don't have a centralized place to find these defines. We already got like a big chunk of defines here, a big chunk of defines here, and a big chunk of defines here. Like, people are going to look at my code and be like, this is mostly defines. What the hell, man? What the hell are you thinking? And what I'm thinking is column limit. Also, putting the defines here kind of makes the section divider a little bit more pronounced, which I think is somewhat of a plus sometimes. Let's also give it a little checksum. It's only 2 things. It's not really like we need a checksum, but since we have enough space to do it, it also creates kind of a visual bracket around the region. Right? This is a bracket facing downwards, and this is a bracket facing upwards. If we look at just the comment characters, we have kind of a line here and a line here like that. And then on the top we have a line like this and a line like this in the comments. So visually we have this bracket that is enclosing the section. Let's do one more thing. Zeros should always use the min, and ones should always use the max. Therefore, when we look at the coloring here, we shouldn't see any interlacing of color on these lines. Kind of screwed up here, though. We have interlacing because of the 128. Let's give it another shot, now that I realize that. We'll have to be a little bit more granular here. It's an x0, so we're going to use min. And the y0 is also 0, so we're going to use min. The ones use a max. The ones use a max. Are all the colors lined up? Is there any interlacing on a single line? We don't see any interlacing on a single line. Therefore, we can be pretty confident we didn't make any mistakes there. So that was very tedious, the way we did that. But the idea is, mistakes in this kind of logic are going to make you want to rip out your hair if you try to run the code and you're like, why the hell isn't this working? Because of that, really you have to spend the time, you're going to have to spend the time eventually. You can either spend the time debugging and hating your life, or you can spend the time now going nice and slow, taking your time. And yeah, you're coding slower, you're taking your time, but at least you know it's going to be right the first time, and you're not going to be like, what the hell later. You're going to be like, you took your time to do it quality, and now you're not gonna pay for it later. So that's pretty good there. Now the question is, what the hell are we doing over here? And we know what we're doing here. The question is, do we want to use these, or do we want to use the... I think we want to use... Instead of the long-handed, we had room to use the long-handed, but I think using the long-handed here just makes it kind of confusing, because we're switching between... If we're gonna use short-handed here, we should stick to short-handed consistently in this section. And also, when we highlight these, they're being referenced in here, but we can't see them being referenced because we're not using our shorthanded macros. If we're going to define a macro to shorthanded hand something, even if we have room, we should still stick to the shorthand. Particularly because right now, if we highlight these different colors, and we look in this section now, we can see everywhere that stuff is being used. We can see the cyan, orange, and yellow. Cyan, orange, and yellow. And that's really going to help us. We can also go like this. We can highlight each side and compare in this way as well. And make sure that we see cyan and orange, cyan and orange, cyan and orange. So all of these are correctly set up. What is this, though? Dir any. Is dir any up here? Where is dir any? Dir any seems to... It's not really used here. Dir any is going to be good because if the dir any flag is not set when we're doing our texture push, then we don't do the texture push because nothing has changed. The cell 512. Got it. So we're marking the exact cell that we're using as dirty. This is actually not really needed. It's more of a redundancy. When we are actually doing the push of the texture, and we are looking at the dirty rectangles. Oh no, because when we're looking at the dirty rectangles, some of those cells might not be dirty, right? The dirty rectangle, for example, let's say we're over here, and we set something in this cell. We set something in the extreme cells. We set something here, and we set something here. So the dirty rectangle now has to cover all of this. So the dirty rectangle is going to scan through every single cell because it hits the entire bounds. But only these cells are marked as dirty, and therefore those are the only ones that get updated. Oh, well, it doesn't really matter here so much, does it? Yeah, it doesn't really matter here so much. It really matters in these smaller cells, I think. Yeah? Yeah, because we're going to go individually for each one of these cells, we're going to do a subtexture push for each one of these cells. There's a little bit of extra redundancy where it doesn't matter. We have a little bit more, I think we have a little bit more information than we actually need. And this could probably be foregone. Also, this is cell. Okay, these are the dirty cell flags. And these are the rectangles. Those are the rectangular regions. Mark individual cells as dirty. So that's what we're doing here. We're marking the individual cells as dirty. And it's just a one-off thing. Because it's whatever we have inputted into the function is what we're going to use. Now, we could use another optimization where if the value hasn't actually changed when we set it, we could ignore marking the thing as dirty. But that's not going to be often enough of a case where I think it would be useful. I gotta take a break, so we're gonna put a timer here. And I'll be back. We're gonna give it 15 minutes. And we'll, actually this time we'll remember to set our screen to break time.
4, so we do have a lot more Overwatch to be played, and Control is kind of that great equal.
That and that. Yeah, that is improved. All right. We go through the same steps. All right. We get the angular velocity. Okay. Then we get, well, yeah, wait, what? I was watching you last night on my I'm not allowed to code day Sunday. It was my girlfriend's PS4 and I wasn't allowed to say anything in chat because of her username. Hey, thanks, man. Hey, Kanji, how you doing? What was I doing last night? Dude, last night I was so brain dead. I feel like I've been brain dead the past couple months. I decided I'm gonna change my diet or something. I don't know. But I need to fix that. But yeah, thanks, man. The viewers matter. I was thinking you could benefit from writing test code for some functions. Avoid sugar. Yeah, test code for some functions. I think you're right. I have some test functions for my matrices. But nothing else yet. I usually avoid writing tests until I get things solid. But like right now I feel like the game is not figured out, but the matrix math is. I could probably write another test for the placing things on objects. That would be a good test for now. Let me think what else. Oh yeah, and damaging things. That would be a good test. Yeah, that's all probably a good idea. Sugar brain needs glucose less from. So what I started doing, what I'm gonna do is when I drink coffee in the morning, I'm gonna have basically black coffee. I tried to look some stuff up yesterday about how to make my brain less scattered, and I read about something called what the fuck was it called? Some type of coffee It was some dumb name. Cream, pure cream. Apparently cream is not even good for you. I'm trying to find the name. Found it. Bulletproof coffee. That is good for you. Yes. Yeah, butter coffee. Exactly. Yeah, that's it. Yeah, so that's what I read. So I bought stuff to do that. I don't know. I think you're not supposed to use store butter. Like, you're supposed to use special grass-fed butter because it has vitamins or something. But yeah, you put like butter in the coffee, and then you put some special brain oil, and then apparently it helps. Heavy whipping cream is what you use for the fat. That's interesting. I actually did butter coffee today, but I only had the store-bought butter, but I figured like the purpose of the butter is fat, right? So like it's the same thing, just without the vitamins that probably barely matter. But I think I do feel better today than I have like the past couple weeks. I also woke up earlier today. That's good. So that's gonna be what I try to do from now on, I think. Yeah, I feel like there is a point in my life where all this shit I'm doing now would have been so easy, and I'm past that point. And that's not good. I mean, granted, the stuff is pretty complicated, but yeah. Okay, what's next? This thing I'm doing now, I don't know how long you've been watching, but what I'm doing now is this little thing. Do you maybe remember how when you used to move this what would you call that? I don't know, intersection used to lag behind, and now it doesn't. It's missing something, and that was very hard. Slid around the polygon edges. Yep. I'll show you. Now it's perfect. Amazing, right? Actually incredible. I should not spend money, right? And I would have literally bet $100 I couldn't have gotten it to this state that it's at. Because really, this is just a completely disconnected polygon. It has no connection to this at all. And it's staying perfectly in sync. And so the way I did that was I got the velocity, I got the acceleration of the body. And first thing I did was I just applied it to this, right? As an offset to the desired position. That didn't work because the offset jumps. Or yeah, so you right when you start accelerating, it like, you know, snaps kind of as you'd expect. And also, this thing has smoothing code that makes the snapping even worse. So the first snap, which is already the most extreme, is multiplicatively the most extreme. So what I ended up doing was some like bastardization of this delta force application math in the desired position code. So yeah, basically it's kind of the same thing. You're calculating the delta and then you're smoothing down the acceleration value in like a trailing way. So you know what I mean? This is a good graph for it, like that. And now this area is your acceleration. And that actually worked perfectly. I just tweaked this value until it worked, the magic number, and it's perfect. Trying to get them to follow each other exactly rather than hard linking together. Yeah, and they were already following each other exactly, but this one connection did not. Because the rest follow each other exactly by predicting where they want to go and trying to move there. And this one has no prediction. This is the actual physics body that you're applying acceleration to. So I had to like hack that prediction using the acceleration values I give it. And I would not have thought that was possible, but it works. Or better at calculus thinking than I am. I don't know, man. I've forgotten so much math. This is like my math logic now is like, yeah, that graph is the shape I want. Let me just mess with the numbers until it works. But so that works. Now I'm working on rotation. Oh, the other complicated thing with it. I do know the acceleration I'm applying to it, but I don't know the external acceleration. And the external acceleration, I can only calculate 1 frame late. So I have more complicated math to get the actual external acceleration, subtract my previous frame's manually applied acceleration, and add back the difference of the non-manual acceleration. And that makes it so it's perfect, 0 frames late, manually applied acceleration correction, and almost perfect 1 frame late delta external applied acceleration correction. Yeah, whatever. So it works. Amazing. Weirdo Desmos. What is this? Is this the, I think someone linked me. Oh, I do know this, yeah. This is the really nice graph, right? Yeah. I use this for shaders sometimes. You do whatever, and then you somehow, I forgot, use that graph in there. I forgot how you do that, but yeah, it's a good thing. I've just been using Wolfram Alpha for these things, which is all right. Gotta get going, keep up the good fight. Thanks, man. Thanks for stopping in. Appreciate you.
Bottom screen. There we go. Okay, so where are we? We got this logic going for marking everything as dirty, and that looks good to me. We see the cell regions here, 512, 128, and 32. This is a 16 cell array, 16 cell array, and 256 cell array, so that is proper. That's good. All of this is good dirty sector management. The dirty sector management, I'd say that is done. The dirty sector management is, that logic is finished. Let's see our checksums. We got 13 and 13 here. Our min and max, we got 13 and we got 2 and 2. We need to, where are we going to use these now? We've marked them dirty, now we need to mark them as clean somewhere, correct? Let's go into the TAUSYNC. Let's open up both of the files just in case. Fairly certain that TAUSYNC is a data-only class. Sorry, a function-only library. I keep on saying class, but I mean library. However, it does use values from we can make a note of what's going on here. Since there is no data here, does that make it a functor? I don't know if functor is the correct word for this, but we'll just, that's what we'll call it, dude. Or, no, we're not going to call it functor, but whatever, doesn't matter. The function files here, we got an init none here. We're going to have two functions. We're going to call this section GPU sync. And just because we call the section GPU sync does not mean that the functions inside need to be called exactly what the section divider is called. Sometimes we'll do that, but also sometimes we just want the section divider to provide some other information or phrase the information in another way to help people grasp it. It's easier to understand things when they're explained in multiple ways. We're going to call it TAUSYNC run, because really this should only be doing one thing. This whole entire library only has one job, and it's the essence of do one thing and do one well, because it's really only one function. This is going to be private, and this is going to be public. The private version, or the public version, is going to have a early exit condition. This any flag. If that flag is set, then we will actually run the syncing function. Private function, basically a force sync. This is basically a force sync because the private version will not have this flag check. The reason for that is when we're coding, if we need to do a little bit of debugging, we can just change the all capital to all lowercase, and then we're force syncing. Now, as we're force syncing, this might be a little bit too rudimentary. I don't know, because we still gonna have to look at the dirty rectangle regions here. So maybe it's not quite a force sync. Maybe this comment is wrong. We have a public and private one, and the public version is slightly more guarded than the private version. How are we going to do this? First of all, we're already assuming that it's dirty by the time we're getting in here. Assumes something is dirty. Okay. These cells here, we want to iterate through all these cells. We need a loop that we need a triply nested loop here, and we need to think about what are we going to call our variables. We could just call it A, B, and C. I don't know if that's the best way to do it. For less than or equal to 16 and cells A, B, and C, right? These cells are, well, the iterator for them, the index accessor could be int32. There's a pretty good rule of thumb to only use unsigned when you're actually dealing with bits. And also in the Google style guide, they mentioned that you don't want to use unsigned types for loops because the problems that it can cause using an unsigned value for a loop kind of outweigh any benefit you would get from using a smaller unsigned type. And we know that we have half the range when we use an integer, right? Because we have half negatives and half positives. But we're only looping through 0 to 16. So that's fine. Also, this is wrong. First of all, this has to be 256. Secondly, well, we were just cutting and pasting, so that makes sense that it would be the way it is. But we want to write it this way so that when we are looking at it, we can be like, oh yeah, 16, these are the bounds. You want to be able to connect these numbers here to the numbers here a little bit easier. So we'll put it in like this and then -1 here. And then we can use less than or equal to. Therefore, the loop is inclusive bounds. Now, you don't have to use inclusive bounds in your loop. Most programmers don't actually use inclusive bounds. They use a half-open range, usually. A half-open range means that it's inclusive on one side, but exclusive on another. It's half-open. It's because it's half-open, right? Open range is... God, which one's which? Open range and close range? I don't remember which is which. But, you know, in a range, usually it's like, this is 1-to-1 inclusive, and this is 1-to-1 exclusive. So this would just be 0 to 0. This would be 0 to 0. This would be, or this wouldn't be 0 to 0. This would just be nothing, right? Because you go 1-to-1 with, but you don't include 1. Well, this all would be nothing. Well, this would at least hit 1, and this is nonsense. Let's write it differently. Let's say 1 to 2. 1 to 2. This includes 1 and 2. Actually, let's do this. This includes 1, 2, and 3. And this range here denoted like this when we're talking about mathematics, this just includes 2, because it doesn't include the anything, because you have these soft brackets. And if we do something like this, usually in most programming code, the loops are actually this mathematically. It is a closed range, it's inclusive at the start, and then it's exclusive at the end. So, well, hold on, like this. So this is 1, so these are all the same. Well, this is 1 to 2. This is 1 to, this is 2 to 2. This is 2 to 2. This is 1 to 3, and this is 1 to 2. Right? In terms of the what numbers are actually going to be hit. Oh, this is just 2. And this one is 1, 2, I believe. Alright, so that's the difference in the notation there. Let's just get rid of that. Let's not populate our code with random miscellaneous comments. But you need to be aware of what kind of ranges you're using. I usually like to keep everything inclusive just because my brain just works best with inclusive ranges, so... Anyways, as we're going through all of these, we want to loop through... So actually, these loops are actually going to be... They're not going to be stacked on each other like this. We actually do need to get in there and do something at each one of these steps. At this CA phase, we're taking the we're going to look at this. This is actually wrong. Our whole premise here is wrong. So we have these 16 cells here, right? Well, if there's 16 cells here, then there's not then it's not just 16 cells here. This is actually like should be an array of 16 times 16 cells. If we're actually gonna like subdivide, we have made a fatal design flaw in how we're doing this. But now we need to reevaluate our life. So I'm gonna have a piece of beef jerky and think about this. Okay. This is CO4. It's, these are 16 collections of 4x4 cells. C16, 250, ooh. Mm-mm. $256 is totally wrong. Okay, I see. 16 by 16. 16 by 16, 256. 4 times 4, 16. So that's why that's there. And at the top level, we just need a flag on or off at the top level. Right? There's nothing nested. But then this has to be kind of in reference to this. This is 4 times 4 cells, that's 16. This is 16 times 16, that's 256. So now we just don't know what the hell we're doing right now. We so thought we had it figured out, and now we're just like, what? I mean, that looks about right. It's just... So cell 128 contains a whole bunch of structs that are... Let's move this over. Since we need to look at our diagrams, let's move this over here and look at this and compare it to what we're doing here. At this top level, when we need a dirty flag, we just need one dirty flag for each one of these slots here, right? So it's a 16 slots because it's 4 by 4, right? 4 by 4. And that's all the flags we need. Now, if one of these is dirty, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 16 things we can drill into here for getting into we need one of these subcells. Okay, I see. I see. I see. Another helper struct. We need a 4 by 4. And we also need a 16 by 16. Four by 4 cells. And this is 16 by 16 cells. Okay. The struct also needs one semicolon at the end of it. We want to know, when we're looking at each one of these, we want to know if these individual cells are dirty, correct? Let's actually, we have these different levels. We should actually mark these by what level they are. We got level A, level B, and we also have a level C. There might be some code duplication this way, but it's going to be easier for me to wrap my head around if we do it this way. So we're going to do it this way. This needs to be 04 and 04. We're going to say this is level A, this is level B here, and finally the deepest level is level C. Level... Tau, sub, and var. Right, so let's put all the things that kind of identify what we're looking at. So a 4x4 tau, 4x4 sub, right? Because this tau section is 4x4. Sub is 4x4, and var is 4x4. We could also say, if we really want to be... did we name things like Tau 512 and whatever? How do we do that? So down here we have like Tau, cell 512, cell 128, cell whatever. Let's just add 512 to here. Let's just add all of the relevant measurements. So it's a 512 by 512 and a 128 by 128. And this last one is 32 by 32. And these measurements are here, so are our pixels. So we could say pix 512 and pix 128 and pix 128. That's kind of like, that is a little ridiculous though. Where how are we going to use this anywhere if we are so goddamn verbose? I think we could call this love. Level A, level B, and level C. Okay. The highest level thing has things in it, right? So we have to flip this around. So level A, the top level needs to be at the bottom because we're going to order it without using forward declarations. So things are going to be ordered backwards. So this right here is outermost top nesting level. This is the outermost level. We want a way that we can denote this where everything is kind of glued together nicely. Lowest slash deepest slash innermost. Okay. So this is C. This is B. And this is A, right? It's all backwards because of the nesting levels here. Every one of these is going to have a is dirty. So U08 is dirty. Each one of these. Because if we want to know if we should drill down deeper, we got to know if the rectangle itself is dirty, correct? And then within there, we need to define we're going to define levels A, B, and C. So we could have a nested structure, or we could we can have it unrolled over here. So rather than having these things mention each other, I think we can get away with doing it unrolled. I could be wrong. I'm not certain on the organization here. Let's put these down here though, because we're gonna need to reference them. And these are very long-handed, so it'd be nice just to 1, 2, 3. Be nice just to be able to reference them shorthanded. Oh, that's not... Come on, just put it where it goes. Okay, so these different levels. The first thing is the outer level, level A, and there are 16 by 16 level A cells. Okay. This actually has much bigger memory footprint than what I was thinking it would have, because we're almost making like a full-blown quad tree-like structure here. So everything we wrote earlier, it had a faulty principle behind it. It's only the outermost level that we're going to keep track of. Level A, like all the other levels, are within this. And the region rectangles that we're going to use are also within this. So every time we do a GL subtexture update, it's the coarsest granularity we're going to get is a 32 by 32 chunk. Is that misguided? Is that a bad idea? I don't know. I don't know how slow are individual calls. Alright, but now that we kind of see what's going on here, and that we were totally misguided, yes, we do want an isDirty flag for level A here. And we can put, we can reference the diagram here. Right? That way we know what cell are we trying to mark dirty right now. And these are the cell names. So when we're looking at the diagram and we want to know what we're marking dirty in that diagram, we can just grab onto these diagram names and be in good standing for having our C. We can actually say like C TAUDEPO.d, right? We have enough room where we can even put where to find the diagram as well. When we're at the outermost level here, we need an array of 16 cells that are of the next level down. And we're really going to need to create these same these same defines we created for level A, B, C. We need to create them up here. Level A, B, and C, because it's just a lot of right, that's a lot of clutter. We just want to know what level they are. the nesting level is the most important aspect. So we're going to rename them as the shorthand things here. And we know that the level A here, and we could even, now that we have these levels here, we could be really weird, and we could name these LA, right? We could, actually, that might actually make sense. So, level A, level B, level C. Define this, which is that. So this is the actual struct name. That is kind of weird, because we're never going to be able to find the... If we do it like that, we're never going to be able to find the... If we write it like that, if somebody's trying to find the actual struct in the code, it's going to be a lot harder to find it. So instead of saying level A, instead of saying it like that, what we could do is nesting level C. We could say, we could give this something like a little indentation like that, and then we could make a little comment here that this is LA. Actually, I think we're gonna go with that. So, right, we'll keep the shorthand name kind of in comments here, like that. Struct LC. Okay, so we're like using up all of our space here, but we see LA, LB, and LC. It feels like a little unaligned here. Yeah, that's a little unaligned. How did that happen? What did we screw up? Okay, I see we're kind of not aligned. Oh, is there... So we have some inconsistencies. Let's make sure that everything is kind of consistent. Okay, that's consistent. So we're looking at this LA, LB, LC. So within LA, now that we can kind of like see what we're looking at, we know that the outermost level needs to reference one deeper than itself. And how many cells do we have? We got 16. So we know we need a struct LB, and the struct name is we could call it, what would we name it so that we don't... What would we rename it so that when we're refactoring, we can kind of see what's here, right? So we have these 16 cells. So the original intention was we have these 16 cells that we can drill into, correct? Yeah, I think that's the intention. So let's try to... It's not the best naming convention, but I think that if we... Cell 512, and then there's like 16 of them. Cell 512, 16. It's not the best naming convention, but it'll help us kind of make the connection between this and this. Yeah, it's kind of ugly. And then when we're down here, so we need the same thing here. We need like a struct LC, so we're going to go reference one deeper. In LC, there's 16 of them. Instead of cell 512, it's cell 128, because it's going to be this whole 128 by 128 region that we're drilling into. So cell 128, and there are also 16 of those cells. And when we get down to the deepest level here, when we're inside of level C, once we're inside of level C, we just need... we can finally do just a UO8, right? We're in the deepest level, there's nothing more to subdivide. Then the deepest cell type was called cell 032. Cell 032. For these cells, it's 16 by 16, so there's 256 of them. 256. So we see the 16, 16, 256, and the 16, 16, 256, right? When we go from the outermost to the innermost, same thing, outermost to innermost, we get 16, 16 to 256. I think it might be a little bit easier if we actually put the struct keyword in front of these. Because we're only using it for the struct. And if we do that and we get rid of the struct keyword in front of here, what helps now is we see the these different types kind of line up with each other, and we can more easily see what's going on there. And if we add 2 spaces here, then we can have the... well, actually, we still have some more work to do. Can we... okay, those braces line up. Do these braces line up, or are we off here? So we're still off. It looks like we added a little bit of extra space here. And the 1s column, 10s column, and 100 column. So they all line up correctly now. Right now, though, we see that the way we wrote it here is we didn't add any extra padding. So we should get rid of that extra padding and remove 1 space on each side. Remove 1 space on each side so that if we take this, we can see, yeah, the similar things that we already made in that other piece of code are going to light up. So we could keep this for reference because this is kind of what we're trying to do, but it was kind of misguided. And now we need a dirty rectangle. So all of these need dirty rectangles, and we see that there's a TYP, and we can just call it rec. We can call it struct rec. We can put it up here. And then over here we'll undef it. So within here, these individual cells, they all have is dirty markers. Except for these cells. These cells are just... are... 256 is dirty. To not be confused here, right? Because we're using is dirty, and then we're in here, and then we're looking at all these cells. All these cells are a collection of is dirty flags. So we also need a rectangle. And this rectangle, we should keep the same naming convention. So 512, 128, 32, 512, 128, 32. So the convention here is just these are paired arrays. That are going to tell us so this is a 4x4 dirty cell marker grid. So these rectangles, these are paired arrays. We can make a note of that. At paired arrays. And actually, let's do it like this. Paired arrays, and then up here, this is also a paired array. And then we're going to make a paired array here as well, or are we actually, like, are we done? Well, these are dirty flags, so we don't need a rectangle, do we? Nope, we still need a rectangle because we have these dirty flags. We don't want to go through all 256. We would like to have some type of optimization. We don't have to go through all 256. So we'll use a cell 032 for that. Or not cell 032, but rec 032. So rec 032, and are there still, how many of these are there? Well, it's 256 individual cells, but well, hold on. These rectangles are supposed to, this rectangle is supposed to be a summary of what's here. It's not supposed to be a duplication of what's here. That makes no sense. So it's this is a 4x4 cells make 16 array slots. Dirty cell bounding box. Okay. So this is a dirty cell bounding box. 4x4 cells is 16 array slots. Same thing here. We only need one of these. When we're at this outer nesting level here, we're looking at these and we want to see, is this dirty, is this dirty, is this dirty, is this dirty, right? We want to look at that 16 different times, and that's why we have this thing, because it has an is dirty flag that we can check. And if it's dirty, then we want to go deeper into it. This struct here is just used, so instead of checking each one of these individually, if this bounding rectangle is selecting, say, these, then we only have to look at those. And that's what that is for. So we only need 16 by 16. Now when we go down deeper, one deeper, so here's level B. We could make a note here. This is level A. Level A. And we could actually just do like a little, we could do like a little dash kind of separator line here to make a note of what's going on here. I don't know if it's the best way to do this, but we could, yeah, we could do this and level A, and then over here, what we could do is where we're kind of like or crossing the level, we could have this line kind of like go through level B. So now we're crossing into level B. Let's take this again. And then finally here, we're crossing into level C. And I like that because we should probably move this over. If that's the way we're gonna roll, we should probably move it over one. That way we have the, I think just aesthetically, can't pronounce words. Aesthetically, the diagram just looks a little bit better with the arrows kind of lined up with that, with the dash line. But yeah, level C, and we know the different levels. End. No. And is there some type of line? I guess for some type of consistency, I feel kind of like it needs some type of dividing line, but I don't know. It's... Yeah, okay, I think that looks good. I mean, it's not... maybe it could use a little bit of something else, but yeah, and no nesting. And now we can see these different nesting levels in our diagram, and I think that is going to help when we're trying to visualize what's going here. So let's look up here at our top nesting level, 512. We have 16 cells on this 512 by 512 block of memory. And we're going to need a rectangle object. We're going to call it rec512 to represent this. Within rec512, it's just going to help us optimize which of the cells we check. When we get into one of these cells specifically, that is an instance of LB. So we can go up to LB, and this whole thing is LB. And we can see if this whole thing is dirty or not, right? If this whole thing is not dirty, then we don't dive any deeper into it. And this is the flag that's going to check that. Otherwise, we'll check for dirty cells. And when we check for dirty cells, we're going to look at rec128. And rec128 is going to let us kind of like say, look over this, and we'll say, are you dirty? 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 And those are you dirty questions we're asking are coming from this is dirty flag. And if any one of those are dirty, then we're going to drill down into the lowest level. So we're going to drill back down into here. And from that, we have 256 flags here. Because it's a 16 by 16. Now we already see that this is 16 by 16 grid of it's a little bit confusing to look at, and I don't know if this is the best way, but this 256 is dirty flags is a 16 by 16 grid, right? Because this is a 16 by 16 grid overlay of these 32 by 32 pixels. So this 32 here represents the 32 by 32 pixel regions, right? This is 32 by 32. This here is 128 by 128, and this is 512 by 512. And that's what these numbers here are representing. So all this stuff is this dirty any flag, though, however, this we get to keep this. Dirty any is looking at this outermost thing and saying, are you dirty? That's what dirty any is doing. And, well, actually, this LA okay, so we don't have, we made this nice little nested tree structure, but we don't actually have any instance of it. So this dirty any is going to actually be replaced by this object. This is going to be our dirty any variable. So in here, it's just an LA and AAC 2020 TAUDIRT Do you want to call it dir any, or do you want to call it like dir root? I think we should just call it dir any. The reasoning for that. Also, if we really want to abbreviate it like this, we gotta put struct in front of here. The reason we want to call it dir any is so that when we're refactoring the mess we wrote, then we don't have as much mental indirection. And we only have one of these, right? We only have one of these. We just have this top level node, LA. It represents this 512 by 512 memory region. Yes, correct. And we can just initialize everything to 0 inside there, and we're good with that. So this looks good now. Now the problem is that our logic for marking everything is, the logic is totally wrong. And the logic might be complicated enough to where it makes sense to start... it makes sense to offboard this to a dirty region marker function. Like, it's finally got to the phase where I don't even know how this code works anymore. I think this code is good for reference, so we're going to take this, and we're going to take the dirty sector management code, and we're going to put it into the hashtag documentation. Because it's good for reference, it's just not the correct... It's not correct. We had a faulty premise where we weren't nesting everything correctly. And then all of this here... We can take this... here. We can remove this because this was like an afterthought, but we can take all of this and put it into our collection of So this code has the right idea. Let's actually put these types back to And this is a rec, and a rec. We should also make a note of, well, what kind of rectangles are these? If we look in the TAUDIRT, we have that helper rectangle. We can take that and we can put it into our documentation here. Rectangular. What kind? So. Okay. So we have this data that we're kind of working with. But this is wrong. This is not the correct these are not the correct calculations. They were close, but they weren't correct. So we're going to keep these here for reference. These calculations for So it's really a Heka-Kaidekish kind of tree. It's not really a quad tree. But quad tree is probably a good enough phrase for what we're doing. And then in here, we can actually we can get rid of all this stuff here. So the dirt var flags are actually these, right? It's actually like a whole section. We can just do a dash line I1 X64. We can just do a dash line into this section. Or dirty markers. Well, actually, no, these are still. We're going to change things a bit. We just want divisions between these sections that make sense. So saying helper and rect and then helper dirty markers, I think is a good way to go. And this rec whatever, rec this, rec that, we don't need that here. We actually need that here. And the U08, I believe, we use U08 everywhere, so we can take this and use it here, and then undef U08 here. Oh, actually, we don't have that as a thing yet, so undef U08. And then all these are just there, right? Yeah. So I'm just trying to get everything to just be kind of like properly organized. And then finally we have all this stuff, all these structs and things. And then we just have one piece of data. And that one piece of data is the... And where are you? It's... So let's look in here. We kind of saved what we were doing. And there was one variable, this one right here, the isDirtyAny flag. Let's make sure we didn't, like, forget it somewhere. Nope, we didn't forget it somewhere. The only member variable. The only variable in this file. The only variable in this file is this. The question is it a good idea to have the only variable in this file buried all the way down here? So you're looking at all this, and you get all these details. I think it would make sense to do a forward declaration so that we can use it right here. And the only variable is this LA thing. We can actually use this define here. And then undef LA. Oh, not with that. This will be struct whatever this. And I don't know if we can initialize it like that. Are we allowed to do that? If we're gonna forward declare it, can we do that? Or is that not allowed because we don't have the oh, got it. That's what we're gonna do. We're gonna take this section and we're actually gonna duplicate it. We're gonna put it down here. And here is where we're actually going to initialize it. Up here, we're going to extern it. That's all we're going to do. We're going to extern it and just say see bottom of file. Because do we have these levels correct? Because it looks like we might not have these. It looks like we might have these defines wrong. Level A should be... Oh, yeah, we even have A, B, and C, and then we have these inverted. We should, first of all, just rename it to A, B, and C. And then if we really want to... I do kind of like having them in the A, B, C kind of order. Even though the way we nest them is kind of backwards, but... A, B, and C. Now, is this correct? So this is not correct. It looks like we kind of cut and paste everywhere, and we got everything wrong. Okay. So now we have this... So I'm noticing that we have this LA in here, but there's no way to confirm that in here. So anywhere we see the lev, I think it's going to make more sense to keep a L like that. Therefore, it's just going to be easier to make the mental connection when we're trying to look at the shorthand. When we try to look at the shorthand, we can see the token. We can see the subtoken that we're using. So if we want to highlight the LA, the LB, and the LC, we can see LA, LB, and LC inside of these larger, these ridiculously large names here. We can actually see what's in them. A, B, and C. Okay, yeah, C is right there. Extern. Is this correct? This is not correct. Actually, it even says Lev C. We're obviously missing some of these levs. Let's see if we can find any... nope, it's just this one that's wrong. And it's a LA, so this is a level A. We can see the LA in there. Let's copy that, and let's paste it here. So level A is the outermost level. And this is where we're actually going to declare it at file scope and use it. And we use the same section divider name up here. The idea is that we want to be able to see it right where it's used. I don't know what we call it. Intern bottom. This section needs some type of comment. It needs a that's kind of what I mean there. These calculations here, we should reference them we'll just do a first TAUDIRT attempt was wrong. So right here, this is my first attempt at doing this, and it was not correct. All this math is not correct. It's close to correct. We can refactor it to be proper.
John Mark,
Yeah.
at 9:10, we're gonna light candles and all that stuff.
Okay.
All right.
So this is... I gotta set a timer. I need to set a timer. 9:10, so 12 minutes, 22 minutes. So timer, let's just set a timer for 20 minutes. When that timer goes off, I have to go do things, religious things. I'm not a religious person, but it seems that other people in the household kind of are. Okay. So let's keep on going here. Looks like my friend Josh saw what I'm working on, so that's cool. Okay, we're gonna have to... I'm gonna move over this little documentation file. I'm gonna move it over to another screen, which you can't see, just so that I have a place to reference it, because I need a lot of reference here. I gotta actually reference this old algorithm, and we have to fix what we screwed up with the logic. Right now, we got the correct structure now. And in TAUDEPO is where we are... Well, TAUDEPO is not where we're... Is it? No, TAUDEPO is where we're setting stuff? No, TAUDEPO is the... Where's the setter logic? Oh yeah, it's in the put. We want to look at the puts. Oh, there's our unit test. And I'm lost. Init, logging and halting, a getter, and a putter. Yeah, we cut it all out of here. Got it. Yeah, so we're even losing track of where that was. Let's take this little marker here, and let's put it where we originally had the code for this. And we also had a thing called dirty sector management. They had a little area that was called dirty sector management, and let's keep that original section we had, but it's going to be completely gutted. We're going to take the whole section that had all that code for dirty sector management in here, in the putter, right? Because when we put something, that's when we have to mark something as dirty. If we're just getting it, we don't got to do shit. So, but let's have this, because this gives us more to grab onto and see what was going on before. We could also name the function the dirty sector management. Since this is what it's named already, we could... Well, we don't want to just call it dirty sector management. We want to give it a proper namespace. So this is a private namespace. We can go AAC 2020 TAUDEPO. Does dirty sector management belong in TAUDEPO, or does it actually belong in TAUDIRT? And I think it belongs in TAUDIRT. Oh god, there's already a lot of... Oh, this is the data file, though. Let's move the data file over to the left and see if we have anything in TAUDIRT.f. So TAUDIRT.f. So we have these min and max functions. In TAUDEPO, it already has a lot of logic. I think it makes sense to put the dirty management logic in here. I think that makes sense, so we're gonna do that. It is kind of like a private function in a way, I think. So we're going to give it a all lowercase. Now it's kind of weird to say, oh, it's a private function, but then we're immediately calling it from something else, which would kind of make it not a private function, but a shared function. Or not a shared function, but a friend function. What I really mean when so I guess my idea of private is a little bit different. My idea of private just means... I use private a little bit loosely here. Private just means be careful when you use this. Something about the usage of this is supposed to be restricted. You know what you're doing if you're accessing this. Dirty... Let's call it dirty sector update. we can take all of these. This is all we need. We don't need to know what the actual value is. We just need to set it. These examples here, we don't really need them. We already have them here. This is level A. This is LB. Level B. This is level C. And we're trying to know what we mean there. We can do level A, B, and C. And saw hours of content you uploaded to YouTube, looking cool. Yeah, Discord sometimes goes off and I have no clue why. Okay, so yeah, this dirty sector update like that looks good to me. And the TAUDIRT comes before TAUDEPO. Therefore, we are able to put this in here. We'll call it main logic. Do one thing and do it well. We need a void, and it's going to be dirty sector update like this. We'll figure out the parameters, because we're just going to cut and paste those parameters, whatever they happen to be. Dirty sector update is taking just their unsigned integers that are 8 bits wide. We can just take them, paste them in there, and bam, we got everything we need. We also need to define what a U08 is, and we need to undefine it over here. Okay. Now that we have this function stubbed in, we can start to traverse over the data structure. Then we know this is the basic structure we're trying to loop over here. This is a diagram that's going to help us when we're trying to loop over that data structure. And then I have the old algorithm we wrote on another screen. And I will take that and use it to kind of figure out which parts I can reuse. For instance, I'm looking at the old algorithm I wrote, and it looks to me like this logic right here is still correct. Because we're at that top level, so let's see, we're at this top level, right? And when we're looking at this, and this, we need to convert those to XY positions. Or do we? Do we even need to convert those into XY positions? We may or may not need the XY position. I'm not 100% confident on that. But looking at this, when I'm trying to solve a problem, I find a good approach is to solve all the things you can immediately solve right away, so that you have more knowns, right? You start with some knowns, and then you see the things that you can solve right away, so you solve those right away, and now you have even more knowns. And if the solution is still not obvious, see what else you can solve, and keep on solving what you can solve, reevaluate. And eventually, you'll probably stumble upon, oh, now I have all the information I need. And you may have solved more things than you needed to solve, but now you're in a position where you can whittle away some of the extraneous calculations you made. Right now, I feel this is going to be a needed calculation, so we're going to stick with it. So this XA, YA is for the level A, or LA. And we can make a note of here at level A So I'm making a little annotation above these with a little @ symbol. There, just so I can more easily. Ooh, that's kind of gross. That's kind of like, ugh, but well, also, we don't need this comment in front of here. We don't need these comment characters, correct? Because we're already in a multi-line commented area. What am I doing? So at level B, it tangents here, but that still looks good. So over here, we got the level C. Where's level C? So level C needs to be injected right there. And why do I have another @ symbol? Oh, I kind of surrounded it with an @. That's kind of weird-ish, but level C, level C, level C. That is a little bit it's a little bit cluttered because I just pasted it and didn't line things up. And that's how I did it up above. Levels. So these levels, we can open up in my hashtag documentation. I'm going to move over my hashtag documentation over again. And we're going to take the at level A. We're going to take at level A, B, and C. And create a three thick section here. And just do A, B, and C like that. And once we have these, we could take part of the diagram and repaste it in here for some redundancy. I don't know if that would be a good idea. Not really, because we already have it here. So what we're going to do is we're going to go see diagram in and that's all we need. That's all we need. We don't need to recut and paste. Shorthand notation. LA, LB, LC are shorthand notation for the different nesting levels of our dirty rectangle marking regions. Right. I'm satisfied with that. I'm going to go put it back in another editor on a different screen so I can keep on looking at the old algorithm we wrote that was misguided and fix it up. We now have the level A, B, C markers. And with those, we can take these verbatim and we can reference them over on this side. So it's kind of weird because we're looking at TAUDEPO here, but we're in TAUDIRT here. The reason for that is the structure here is for how we're storing the data, but how we're storing the data directly mirrors how we mark the data as dirty. But we have to use a paired structure. We have to have a complementary structure to store the dirty information, because the actual data here, this is just showing how we're subdividing a 512 by 512 array of pixels. And we can't take that array of pixels and like add like other things into it, because it needs to be a raw array of pixels that we're pushing up to the GPU. So we couldn't even do that if we wanted to. So once we get the dirty XY tiles, we need to kind of drill into everything to figure out where we are. So this cell 512 is wrong. Like these cell things, where are these cell things? These cells, we could fix that though. So the cell 512 is actually now like it is a lookup now. Let's close this sync stuff. Let's close sync right now. We're not worrying about that. The cell 512 is, what is it? It is LA. To get the correct cell 512, we got to do LA. We got to look in LA, and LA has a thing called LB. No, it has this. No, LA has a LB struct array, which is called cell 512. And so to get the cell 512, we can. Yeah, it's actually good that we ripped this into its own function, because we're going to have a lot of defines again. So this cell 512 is actually going to be this guy here, the top level, and we're going to take this as an accessor. And we might as well wrap it like this. So that is pretty meh. Kind of. It's kind of. I don't know how I feel about that. But if we do it like this, then when we're looking at this and we're thinking about the logic here. Now we have the correct cell 512 selected. But it's going to get even more complicated, because the cell 128 is... Let's not do it like that. Like, I'm not against the way we're doing that. We're honing in on the way this needs to be done, but I don't think it needs. We're honing in on the problem. We're getting there. The default. Oh, okay. So it's time to. This is the problem with being awake when everyone else is awake. You gotta like do shit. So timer went off. I gotta go upstairs. So it looks like this stream has been going for like almost 6 hours, and if the stream gets over 10 hours, I can't... Let me just write some shit here. And bring attention to these guys. These are the guys I gotta look at when I get back. If the stream goes over 10 hours, then I can't upload it to YouTube, and I made that mistake before. And Mondays are the days I go a little bit too long because I drink a lot of coffee on Mondays. Therefore, I'm going to stop the stream, and we're going to start the stream over again in maybe half hour to an hour. I don't know how long they're going to fucking keep me. Like, you think it's going to be a little short thing, and it's going to take forever. So, I'm going to stop streaming, and I will be back later if I can figure out how to stop the stream. So let's look at our agenda really quick. Well, we're about to quit here. So the agenda screen. Right now, we are doing the number 15. We're adding the dirty flags. And yeah, we're doing number 15 right now. We're on 15. Item number 15 is what we're doing. To be continued at a later date, we're going to have to change the serial number to 43 when we get back. So hopefully I remember that. It needs to be serial number 43 when we do the next video. So later, I'll be back. 1 hour to 30 minutes, or 30 minutes to 1 hour.